What if a series of cosmic events wasn't a coincidence, but a trail of clues? In September 2025, our solar system sent us a message. A fleet of asteroids making unusually close passes, a mysterious new comet lighting up the twilight sky, and at the center of it all, an ancient visitor from another star system with an impossible chemistry. Coincidence? Or the opening act of something we don't yet understand? In this video, we're going to be the detectives. We'll examine the evidence, piece together the timeline, and explore the chilling question. Was our solar system trying to tell us something? To join our crew of cosmic investigators and never miss a clue, make sure you hit that subscribe button and ring the notification bell so you're always on the case. Now, as we go through the evidence, I want to hear your theories. What's your initial hypothesis? Are you team cosmic coincidence or team deeper connection? Let me know in the comments below. Let the investigation begin. Right now, as you read these words, something is happening in the silent velvet blackness of our solar system. It is something unprecedented, something that has subtly shifted the familiar cosmic clockwork we have come to rely upon. It began as a whisper in the data, a faint smudge of light where none should be. But ever since the object known as 3IA2AS was discovered in the quiet month of July, things have been getting progressively, undeniably, weirder up there. This was no ordinary comet or asteroid, dutifully making its rounds. This was an ancient interstellar visitor, a messenger from a star system light years away, and from the very first moment it entered our lives, it baffled astronomers. Its impossible chemistry, a recipe of elements that defied our understanding of how comets are born, was strange enough. The faint, ethereal green glow that surrounded it was stranger still. But by the crisp autumn weeks of 2025, its alien makeup and ghostly light were no longer the strangest part of its story. The strangest part was what appeared to be following in its wake. Our cosmic neighborhood, usually so predictable in its elegant gravitational dance, had transformed. It was no longer a quiet celestial suburb. It had become a bustling, chaotic highway of converging objects. Clustering patterns emerged that seemed to defy the cold, hard logic of probability. It started with a swarm of 7 comets arriving in close formation, a statistical anomaly that raised eyebrows in observatories from Chile to Hawaii. Then came a fresh wave of asteroids, a fleet of rocky nomads, making unusually close passes by Earth. What we were seeing in the night sky was anything but normal. The quiet hum of the cosmos had been replaced by a rising crescendo of activity, a celestial symphony playing a song we had never heard before. And as the data poured in, as telescopes around the world pivoted to track the sudden influx of cosmic traffic, astronomers had no choice but to start asking the question that felt both thrilling and terrifying. What is 3I Atlas really doing to our solar system? Are we merely witnessing the galaxy's greatest and most improbable coincidence? Or is this the opening act of something far more profound, a drama playing out on a scale that dwarfs human comprehension? Mid-September 2025 was supposed to be a quiet time for the sentinels of the sky. For the men and women who spend their nights staring into the abyss, it was scheduled to be just another month of routine cosmic traffic. They expected the usual assortment of distant, faint objects, the kind of predictable passers-by that astronomers catalog with a calm, mechanical precision before archiving the data and moving on to their next observation. It was a job of immense patience, a slow and steady mapping of our place in the universe. But the universe, it seemed, had other plans. What unfolded in those cool, clear autumn weeks was something entirely different. A celestial parade so grand and so unexpected that it left seasoned scientists scrambling to their telescopes and the public, staring at the heavens wondering if we were witnessing something more than mere chance. The headliner of this cosmic festival arrived first, and it was a monster. They called it Asteroid 2025 FA22, a mountain-sized chunk of primordial rock and metal. Pinpointing its exact dimensions was difficult from such a distance, but the calculations placed it somewhere between 130 and 290 meters, a cross large enough to hold a sports stadium, large enough to alter history. On the 18th of September, it made its grand entrance. 2025 FA-22 swept past Earth at a breathtaking velocity, closing to a distance of just over 2 lunar distances. To put that in perspective, the Moon orbits us from about 384,000 kilometers away. This behemoth came within 835,000 kilometers of our world. In the boundless expanse of space, this was a staggeringly close shave. It was close enough to make headlines around the globe, to have news anchors pointing at graphics of a tumbling rock next to a fragile blue marble. But it was, thankfully, just far enough to let us sleep soundly, to allow us to watch in awe rather than in terror. But here is where the story pivots, where the strange becomes the truly mysterious. FA-22 didn't come alone. This wasn't the typical lone wolf asteroid, a solitary wanderer making its scheduled, predictable appearance on the cosmic stage. Instead, its arrival felt more like opening night at a grand celestial theater, with a whole cast of performers ready to take the stage in rapid, almost choreographed succession. The opening act had already made its entrance 3 days earlier. On September 15th, a smaller but still significant near-Earth object, designated 2025 AJ2, had buzzed past our planet. It came much, much closer than the main event. Its trajectory brought it to within just 0.78 lunar distances, a mere 300,000 kilometers from our doorstep. In astronomical terms, that's not a flyby. It's practically a handshake. It slipped between the Earth and the Moon, a silent stone skipping across our pond. These weren't isolated incidents. They were the heralds of a flood. Throughout that same week, as news of FA-22 and RJ-2 filled the airwaves, the global network of space surveillance systems was working overtime. Dozens of additional visitors, each one smaller, but traveling on trajectories that brought them inside the Moon's orbit sublunar distance, visitors painted their ghostly trails across our local neighborhood. Everyone was cataloged, its orbit calculated, its threat level assessed. By the numbers, the sheer volume of traffic was within the realm of what our advanced systems could handle. Yet something about the clustering felt different. It felt unnatural. The timing of these close approaches seemed almost too perfect, too synchronized, as if these ancient wandering stones had somehow coordinated their arrival for maximum dramatic effect. Then came the supporting cast, adding a touch of ethereal beauty to the unfolding drama. While the world watched the asteroids, another performer was quietly preparing for its debut in the evening sky. On September 11th, the sound instrument aboard the SOHO spacecraft, a satellite whose primary job is to watch our sun, detected a faint eruption of hydrogen against the black. It was a comet, a new one, designated C-2025-R2. As it fell inward toward the sun, it began to brighten with astonishing speed. By mid-September, it was approaching naked-eye visibility, a ghostly smudge of light hanging near the constellation Virgo. Amateur astronomers, armed with backyard telescopes and binoculars, began reporting sightings, their forums buzzing with excitement. They described a tail of shimmering dust and gas stretching across the evening sky like a cosmic brushstroke, a celestial masterpiece visible to anyone who knew where to look, as twilight surrendered to the profound darkness of night. But like all comets, it was a fragile beauty. Many such objects, dirty snowballs of ice and rock from the dawn of the solar system, fragment and die under the sun's intense, unforgiving heat. Their fate beyond their closest approach to our star, their perihelion, remained uncertain. They might survive to visit us again in 1,000 years, or they might shatter into a trail of glowing debris, a brief, glittering monument to their stellar careers. Meanwhile, lurking in the background of every astronomical news report was another familiar face, a name that had long been synonymous with cosmic dread: Apophis. Officially designated 99,942 Apophis. This is the asteroid that once topped every planetary defense worry list on Earth. It is a true monster, a 400-meter-wide mountain of rock, scheduled for an uncomfortably, terrifyingly close encounter with our planet. The date is already circled on the calendars of scientists worldwide, April 13th, 2029. That flyby will bring Apophis within a mere 32,000 kilometers of our planet's surface. This is closer than our geostationary satellites, the vital machines that relay our communications and broadcast our television shows. It will be so close that it will be visible with the naked eye, a bright, fast-moving star screaming across the night sky at an almost unbelievable 50,000 kilometers per hour. The reminder of its impending arrival during this already busy month felt like a dark premonition, a ghost of a future threat looming over the present chaos. But the real star of this celestial show, the true source of the deepening mystery, was still waiting in the wings. Hidden among the flood of routine discovery announcements was something that was anything but routine. It was the object that had started it all, 3I TLAS, also known as C2025N1. It had been discovered on July 1st, 2025, by the dedicated Atlas survey team in the clear, high-altitude air of Chile. And this object was profoundly, fundamentally different from everything else crowding our telescopes that September. It wasn't just another asteroid from the belt between Mars and Jupiter. It wasn't another comet from the frozen frontiers of our own solar system family. This was something far more exotic. This was an interstellar visitor, only the third ever confirmed in human history. And it was carrying chemical signatures that would soon challenge everything we thought we knew about how planets, and perhaps even life, are formed throughout the galaxy. When the Atlas team had first spotted it, it was just another fuzzy dot moving against the starfield, one of thousands they cataloged each month. But as follow-up observations from other observatories poured in, as its trajectory was refined with ever greater accuracy, the cold, emotionless mathematics began to tell an extraordinary story. This object was traveling on a hyperbolic orbit. In the language of celestial mechanics, this was a smoking gun. An object with an elliptical orbit is bound by the sun's gravity, destined to circle it forever. But a hyperbolic orbit means the object possesses more than enough velocity to escape our sun's gravitational embrace entirely. It was a cosmic tourist on a one-way trip. It had come from somewhere else, another star system, perhaps light years away across the interstellar dark. And after its brief, fleeting encounter with our solar neighborhood, it would continue on its journey into the cosmic void, never to return. What made 3IATLIS even more remarkable was its timing. It seemed too perfect, too serendipitous to be believed. Its perihelion, its closest and most volatile approach to the Sun, was scheduled for late October 2025, just a few short weeks after the Great September Asteroid Parade. Then, like a performer exiting stage left, it would vanish into the blinding glare of our star, hidden by its overwhelming brightness. But patience, the astronomers knew, would be rewarded. In early December, as Earth's own orbital motion carried us to a better viewing angle, 31ATLAS would re-emerge from behind the sun's brilliant curtain. This would be the moment. This would be our best opportunity to study an authentic, pristine piece of interstellar real estate. The observing window was perfect. A little too perfect, some might say, in hushed tones late at night. The universe, it seemed, had delivered a carefully packaged sample from another star system directly to our astronomical doorstep, complete with optimal viewing conditions and a leisurely timeline for study. The question that hung in the air, unspoken in press releases but whispered in university hallways, was simply, why? Why now? What had drawn all these cosmic wanderers, both local and interstellar, into this single narrow window of time, creating a celestial drama that felt less like a random series of events and more like the opening act of something we couldn't yet begin to comprehend. The sky was more active than it had been in living memory, and at the heart of it all was a mysterious green visitor from a place unknown, pulling our attention, and perhaps much more, along with it. The question lingered in the silent, sterile rooms of observatories, and echoed in the frantic chatter of online forums. Why? Why now? Was there some hidden gravitational confluence, a celestial alignment not predicted by our models, that had drawn these myriad objects into a sudden, spectacular convergence? Or were witnessing the opening act of something far larger, a cosmic drama playing out on timescales so vast they are almost beyond human perception? The human brain is a magnificent and sometimes treacherous thing. It is an instrument exquisitely designed over millennia to detect patterns, a skill that once helped our ancestors spot a predator hiding in the tall grass, or recognize the subtle shift in the stars that heralded a change in seasons. But in the context of the cosmos, a realm of unimaginable scales and random chances, this same pattern recognition system can lead us astray. It can tempt us to find intricate conspiracies in what is merely the chaotic noise of cosmic events, to see the hand of a conductor where there is only the beautiful, indifferent dance of physics. The first, most rational explanation for the September surge was not to be found in the mysterious pull of our interstellar visitor, but in a revolution that was happening right here on Earth. The answer, or at least the beginning of it, lay high in the bone-dry air of the Chilean Andes. Here, on a mountaintop that scrapes the heavens, a new eye had just opened to the universe. The Vera C. Rubin Observatory, a marvel of modern engineering, had captured its first light images in June of 2025. To call it a telescope is an understatement. It is a cosmic sentinel, a wide-eyed watcher capable of scanning the entire accessible sky with a sensitivity and speed that was once the stuff of science fiction. Its mission was not to stare intently at a single, distant galaxy for weeks on end, but to conduct a sweeping, relentless survey, creating a motion picture of the night sky, revealing anything and everything that moved or changed. And in its very first test runs, it had begun to show us just how crowded our cosmic neighborhood truly was. Imagine for a moment that you have lived your entire life in a dimly lit room, your eyes accustomed to the gloom. You can make out the basic shapes of the furniture, the ghosts of objects in the corners. Then, one day, someone flips a switch, and the room is flooded with brilliant, unrelenting light. Suddenly, you see everything. You see the countless motes of dust dancing in the sunbeams, the intricate patterns on the wallpaper you never noticed, the spiderweb in the far corner. The room hasn't changed. The amount of dust hasn't increased. Only your ability to perceive it has. This was the effect of the Vera C. Rubin Observatory. In approximately 10 hours of initial operation, a mere blink of an eye in astronomical time, it had netted thousands of new asteroid detections. It was revealing the true population density of our solar system's small body constituency, a population that had always been there, moving silently in the dark, but had remained largely invisible to our less sensitive instruments. This phenomenon, known as observational bias, became the prime suspect in the case of the September surge. It wasn't necessarily that there were more asteroids, but that our awareness of their presence had increased dramatically. It was as if we had suddenly installed a state-of-the-art security system in a previously unmonitored part of the city. The number of people walking through the area hadn't changed, but the number of alerts on our screen went through the roof. This was the logical, scientific, and most likely explanation. And yet, for some, it didn't feel complete. It felt too neat, too clean. Even accounting for the flood of new data from the Rubin Observatory, the timing felt too convenient, too perfectly orchestrated to dismiss as a simple observational artifact. The way these objects converged the close pass of the mountain-sized FA-22, just days after the whisper-close flyby of RJ-2, all while a new comet lit up the sky and a visitor from another star system was making its grand approach. It felt too much like a story. too much like a performance. The mood among astronomers, the people on the front lines of this unfolding mystery, wasn't fear. It wasn't the panicked, world-ending terror so often depicted in disaster movies. It was something far more potent, an urgent, almost electric curiosity. They were like detectives who had stumbled upon a scene with too many clues, too many threads leading in different directions. The September surge had awakened something in the collective scientific consciousness. It wasn't panic. It was recognition. It was the dawning, humbling realization that our solar system was far more active, far more dynamic, and far more connected to the broader galaxy than we had ever truly imagined. This newfound awareness brought with it a renewed focus on a field that had, until recently, been relegated to the realm of fiction: planetary defense. For decades, the idea of an asteroid impact was a plot device for Hollywood blockbusters. But in the 21st century, it had become a serious, data-driven science. We now possess the technological capability to not only track and characterize these potentially hazardous objects, but to actually do something about them. We could deflect them. The proof had come just a few years earlier, in a moment of breathtaking audacity. NASA's Double Asteroid Redirection Test, or DART mission, had been a stunning success. Humanity had, for the first time, thrown a punch at the cosmos and connected. The spacecraft, a projectile of our own making, had slammed into a small asteroid and successfully altered its trajectory. It was a cosmic game of billiards played on a scale of millions of kilometers, and we had made the shot. As the world watched the September surge, a follow-up mission, the European Space Agency's Hera, was already silently cruising through the void. Its destination was the scene of DART's impact, where it would act as a forensic examiner, studying the results of our cosmic intervention in meticulous detail. Knowledge and preparation, however, are only as good as the warning time they provide. And that inescapable fact raised a host of uncomfortable questions about the visitors we hadn't seen yet. What about the ones still approaching from the direction of the sun, hidden in the blinding glare of our own star, until their final, terrifying approach? This wasn't a hypothetical problem. We had a chilling precedent. The Chelyabinsk event of 2013, when a 20-meter asteroid exploded over a Russian city with the force of a nuclear bomb, had been a stark reminder of this critical vulnerability. No telescope on Earth saw it coming. It had used the sun as a shield, remaining perfectly hidden in the glare until it was already screaming through our atmosphere. If FA-22, an object many times larger and more powerful, had been on a collision course instead of a safe flyby, and if it had come from that sunward blind spot, would we have had enough advanced notice to mount an effective response? Could we have scrambled a mission like DART in time? The honest, unsettling answer was almost certainly no. This was the true, sobering lesson of the September surge. It wasn't just about the objects we saw. It was about the ones we might be missing. And what did 3IATLA, with its alien chemistry and its interstellar origins, tell us about the unseen population of objects drifting silently in the vast, dark ocean between the stars? We were witnessing the opening act of humanity's transition from a single-planet species, looking inward to active participants in galactic-scale phenomena, looking outward with new eyes and a dawning sense of our own fragility. We were beginning to understand our place in the cosmic ecosystem. But first, before we could fully grasp our role as galactic citizens, we needed to understand the raw physical reality of the threats that shared our space. We needed to confront the terrifying power locked within these wandering mountains of rock and ice. We needed to ask the question that the safe passage of asteroid 2025, FA-22, had mercifully allowed us to avoid in reality, but which we now had to face in the stark, unforgiving world of physics and mathematics. If that mountain of rock had not sailed safely past, if its trajectory had been just a fraction of a degree different, if it had hit Earth, what would that impact have actually looked like? To truly understand the drama of September 2025, we must do something our minds are not built for. We must leave the realm of awe and wonder, of celestial parades and mysterious visitors, and step into the cold, brutal calculus of cosmic collision. We must run the simulation. We must write the unforgiving script of what would have happened if asteroid 2025 FA22's trajectory had been just a whisper of a degree different. The mathematics of such an encounter are not abstract. They are the physics of obliteration, and they are unforgiving. When that mountain of rock swept past us on September 18th, a silent ghost at a safe distance of 835,000 kilometers, it was not merely a rock. It was a vessel of unimaginable energy. It carried with it the kinetic energy equivalent of roughly 100 megatons of TNT. Let that number sink in. 100 million tons of high explosive. It's a figure so large it loses all meaning. So let's bring it down to Earth, to a scale of horror we can comprehend. The atomic bomb that leveled the city of Hiroshima in 1945 was a weapon of almost incomprehensible power. The energy carried by asteroid 2025 FA22 was approximately 2,000 times greater. All of that world-shattering force, concentrated in a single, rocky projectile somewhere between 130 and 290 meters across, moving at a speed of 10.8 kilometers per second. But raw energy is only part of the story. It is the beginning of the equation, not the end. What matters most in the terrifying theater of a cosmic impact is how that energy gets delivered to our planet as fragile surface. And that delivery depends entirely on a complex, chaotic dance of physics, a waltz of variables involving the asteroid's atmospheric entry angle, its composition, and a healthy dose of sheer, dumb cosmic luck. The difference between a regional catastrophe and a true global extinction event often comes down to factors as deceptively simple as whether the incoming object is made of solid dense iron or is just a loose collection of gravel and dust held together by gravity. It depends on whether it arrives at a steep, plunging angle, or if it grazes the upper atmosphere like a stone skipping on water. It depends on whether it explodes in the air, miles above the ground, or whether it has the integrity to punch all the way through to the surface. For a stony asteroid like 2025 FA22, the most likely scenario, the one the models screened was the highest probability, would have been an airburst. It would have detonated in a silent, blinding flash somewhere between 5 and 15 kilometers above the ground, never reaching the surface at all. This is not a comforting thought. We have a name for an event like this. We call it Tunguska. In 1908, in a remote, desolate region of Siberia, something detonated in the sky with the force of an estimated 3 to 15 megatons. It flattened over 2,000 square kilometers of forest, felling 80 million trees in a radial pattern, yet it never created a crater. The Tunguska event was a ghost impact, a warning shot from the cosmos. The FA22 scenario would have been that ghost, grown into a monster of biblical proportions. Imagine standing 200 kilometers away from ground zero on a clear, crisp morning. First would come the light, a flash so brilliant it would be brighter than the sun, visible even in broad daylight. It would burn the retinas of anyone unlucky enough to be looking in its direction. Across hundreds of square kilometers, it would ignite clothing, vegetation, and the very wood of people's homes. This thermal pulse, a wave of pure heat traveling at the speed of light, would last for several agonizing seconds, long enough to cause third-degree burns to any exposed skin at distances exceeding 100 kilometers. Then, after the terrible silence of the flash, would come the sound, or rather, the force. The shock wave from a 100 megaton airburst would be a physical blow, a hammer of compressed air moving faster than sound. It would shatter windows across an area the size of a small country. But closer in, it would be far worse. The overpressure wave, The sheer crushing force of the blast would flatten most residential buildings within 50 kilometers of ground zero. It would obliterate towns and villages, leaving nothing but splinters and dust. Out to distances approaching 150 kilometers, it would cause significant, catastrophic structural damage. Even well-built concrete and steel structures would suffer severe damage within this inner destruction zone. Their frames twisted, their walls collapsed. It would be a circle of devastation hundreds of kilometers across, painted on the earth in an instant by a rock that never even touched the ground. But what if the dice had rolled differently? What if Fa-22 wasn't a loose stony rubble pile? What if it had been forged of denser material, a solid chunk of iron and nickel from the core of a long-dead protoplanet? What if it had arrived at a shallower angle, allowing it to survive its fiery atmospheric passage and penetrate deeper before fragmenting? This is the crater scenario, and it presents an entirely different kind of devastation. Using established impact modeling programs, like the aptly named Impact Earth, scientists can paint a chillingly precise picture. A 200-meter iron asteroid striking at 10 kilometers per second wouldn't just create a hole. It would excavate a crater approximately 3 kilometers in diameter and 500 meters deep. The immediate effects for anyone within visual range would be nothing short of apocalyptic. The impact would vaporize the asteroid and an equivalent mass of the Earth's S-crust in a fraction of a second, launching millions of tons of superheated, molten debris on high, ballistic trajectories. This fiery rain would fall back to Earth across thousands of square kilometers, starting fires, melting glass, and turning a vast landscape into a vision of hell. The seismic shock of the impact would register as a magnitude 6.5 earthquake, a violent upheaval that would collapse buildings and trigger landslides across a region hundreds of kilometers wide. It would be an earthquake, a firestorm, and a volcanic eruption, all rolled into one terrible moment. Yet perhaps the most terrifying scenario of all is also the most likely. Over 70% of our planet's surface is covered by water. For any randomly arriving asteroid, an ocean impact is statistically the most probable outcome. And when these cosmic projectiles hit the ocean, they don't simply disappear into the depths with a large splash. They create something far more insidious, far more dangerous: tsunamis. The physics of impact-generated tsunamis are still being refined, but recent modeling has given us a horrifying glimpse of their power. Even a 250-meter asteroid striking the deep ocean would produce initial wave heights exceeding 100 meters at the impact site. A wall of water 30 stories high would erupt from the sea. These waves would then propagate outward at the speed of a jet aircraft, carrying enough energy to remain lethally dangerous across entire ocean basins. A 2025 Fa-22-sized impact in the mid-Atlantic could, in theory, send 10-meter waves that would dwarf any coastal defense, crashing into the coastal cities of 2 continents, from Boston to Barcelona just hours after impact. There is, of course, an important scientific caveat that often gets lost in the disaster scenarios. The open ocean is vast, and a wave's height attenuates with distance. Classic hydrocode simulations show that these tsunami waves lose energy as they travel. A devastating 100-meter wave at the impact site might be reduced to a still terrifying 10 meters by the time it travels 60 kilometers, and it would continue to diminish as it crossed the ocean basin. The devil, as always, is in the details of coastal geography and the shape of the local seafloor, which can refocus and amplify a wave's power with devastating consequences. The final crucial question is one of scale. Would an impact from 2025 Fa-22 have been an extinction-level event? The answer is almost certainly no. An Fa-22 impact would certainly cause unprecedented regional devastation, potentially affecting the lives of millions of people and altering economies for a generation. But it would be unlikely to trigger the kind of global climate effects like an impact winter that would threaten human civilization as a whole. That level of planetary destruction requires much, much larger impactors, objects in the kilometer-plus size range. These are the true planet killers, and they strike, on average, perhaps only once every few 100,000 years. An FA-22 impact would have been a catastrophe, a tragedy on a scale we have never witnessed, but humanity would have survived. It would have been the wound of a century, not the death of a species. This entire terrifying thought experiment serves as a stark reminder of the world we live in. We exist on a beautiful, fragile planet embedded in a cosmic shooting gallery. Most of the debris is harmless, sand grain-sized particles that burn up as picturesque meteor showers. But occasionally, something larger slips through the gaps in our detection network. And as we learned from the Chelyabinsk event in 2013, the most dangerous object isn't necessarily the largest or the fastest. The most dangerous object is the one you never see coming at all. The case of the 2013 Chelyabinsk meteor wasn't just a scientific event. It was a global lesson in humility, delivered without warning. On the morning of February 15th, a 20-meter asteroid, no larger than a 6-story building, entered the Earth's atmosphere over the Ural Mountains in Russia. It exploded in a brilliant airburst, releasing energy equivalent to approximately 500 kilotons of TNT, 30 times more powerful than the Hiroshima bomb. The resulting shockwave injured over 1,500 people, primarily from flying glass, as hundreds of thousands of windows were shattered across the city. The world was treated to a terrifying spectacle, captured on countless dashboard cameras, of what happens when even a relatively small piece of cosmic debris meets modern civilization. But for the planetary defense experts, the real story wasn't the damage it caused. The most concerning aspect of the Chelyabinsk event was the chilling fact that it had arrived completely and utterly undetected. No telescope on Earth, not one of the sophisticated survey systems designed for this exact purpose, saw it coming. The asteroid had approached from the direction of the sun, perfectly hidden in the blinding solar glare until the final, fiery moments before atmospheric entry. This represents one of the fundamental, terrifying blind spots in our current detection network, the sunward approach corridor. It is a vast cone of invisibility pointing away from Earth, a celestial dead zone where even city-killer-sized objects can lurk unseen until they're already upon us. They can arrive with essentially zero warning, turning any potential for a deflection mission into a frantic, last-ditch effort for evacuation and damage control. This is why the September 2025 encounter with asteroid 2025 FA22, for all the anxiety it generated, was also an invaluable gift. Its safe flyby provided a crucial, real-world exercise for the fledgling International Planetary Defense Coordination System. For a brief, tense period after its discovery, the asteroid had appeared on the European Space Agency's official risk assessment list. This list is a carefully curated catalog of objects whose orbits bring them close enough to Earth to warrant continuous monitoring. Early observations always have a degree of uncertainty, and for a short while, FA-22's uncertainty region, the range of possible paths it might take, included a non-zero, albeit tiny, probability of impact. As more observations poured in from around the world, the orbit was refined, the uncertainty shrank, and the impact scenarios were definitively ruled out. FA-22 was then promptly removed from the risk list. This entire process, from initial detection to risk assessment to final clearance, gave the world's space agencies vital practice in the delicate and incredibly difficult art of public communication about potentially hazardous objects. It's a challenge fraught with peril. How do you inform the public about a possible, but unconfirmed, threat without causing widespread panic? How do you convey the nuances of orbital uncertainty to a world that often craves simple, black-and-white answers? How do you coordinate international response efforts when you're dealing with an object that might not even be a threat, and which could, if it were, affect multiple countries with competing interests? These are not just scientific questions. They are deeply human ones. During FA-22's approach, the International Asteroid Warning Network, or IAWN, conducted what amounted to a leave-fire exercise. This global collaboration of observatories, space agencies, and researchers tested their communication protocols and observation coordination procedures in real time. Data was shared instantly across continents. Telescopes were tasked and retasked to gather the critical follow-up observations needed to shrink that uncertainty region. The fact that it was ultimately a false alarm didn't diminish the value of the experience one bit. In fact, it provided something even more valuable, proof that the system, under pressure, could actually work. It showed that global cooperation in the face of a potential cosmic threat was not just a lofty ideal, but a functioning reality. But the exercise also served to highlight the critical gaps that remain in our planetary defense capabilities. In the world of asteroid deflection, lead time is everything. It is the single most important variable. The earlier we detect a potentially hazardous object, the smaller the deflection required to safely alter its trajectory. A gentle, precise nudge, applied years or even decades in advance, can eliminate the need for desperate, high-risk measures at the last minute. It is the difference between gently leaning on a train to switch its track miles before a junction and trying to stop the locomotive with a brick wall just feet from the station. Our current deflection technologies, validated so spectacularly by NASA's DART mission, rely primarily on a technique called kinetic impact. In essence, we are playing cosmic billiards, using a high-speed spacecraft as a cue ball to strike the target asteroid and nudge it into a slightly different, safer orbit. We know the technique works, but its effectiveness depends entirely on having precise knowledge of the target's composition, structure, and rotation state. A solid iron mountain responds very differently to an impact than a loosely packed rubble pile. Getting those calculations wrong could mean the difference between a successful deflection and a catastrophic fragmentation, where we inadvertently turn one large, predictable problem into a shotgun blast of smaller, unpredictable ones. The 2025 FA-22 scenario, even as a near miss, serves as a powerful and sobering reminder that we live on a planet embedded in a dynamic and sometimes violent cosmic environment. The good news is that we are getting much, much better at this celestial neighborhood watch. New survey telescopes, like the revolutionary Vera C. Rubin Observatory, are coming online with an unprecedented capability to detect and track these objects. And critically, a new generation of space-based infrared observatories will soon be deployed to stand guard over that dangerous sunward blind spot. Missions like NASA's Near-Earth Object NEO Surveyor will finally close the detection gap that allowed Chelyabinsk to arrive unannounced, giving us a more complete 360-degree view of any potential threats. Yet just as we have become more proficient at cataloging the familiar threats within our immediate solar system, we have also begun to realize just how much we still don't know about the larger cosmic environment we inhabit. And that brings us back to the heart of the September mystery. It brings us back to the strange, green visitor from another star, 3I-ATLAS. Objects like this remind us that our solar system is not an isolated island fortress. It is more like a busy port, a rest stop along the galactic highway, constantly receiving visitors from the vast, dark spaces between the stars. Which raises an intriguing, almost unsettling question about the September surge. Were we merely witnessing a random clustering of unrelated local objects? A simple coincidence of orbital mechanics and improved detection? Or could there be deeper, unseen connections between the close approach of asteroid 2025, FA-22, the swarm of other near-Earth asteroids, and the mysterious interstellar intruder that was silently stealing the astronomical headlines? Before we can even begin to answer that question, before we can unravel the thread that might connect the local to the interstellar, we need to understand what else was sharing the cosmic stage during those remarkable autumn weeks. Because while FA-22 captured the public's imagination with its raw power and its close shave, another, more ethereal performer was quietly preparing for its own moment in the spotlight. A celestial artist painting a transient masterpiece against the twilight sky, while the world's most powerful computers were running simulations of planetary destruction, and its most advanced tracking systems were standing sentinel against the silent threat of unseen asteroids. Another kind of drama was unfolding in the deepening twilight. This was not a story of raw power and brute force, but one of ethereal, fleeting beauty. While asteroid 2025 FA-22 had captured headlines with its close, menacing approach, another celestial performer was quietly preparing for its debut, and it was stealing the hearts of those who watched the sky not with fear, but with love. It was Comet C 2025 R2, and unlike the predictable, well-mapped trajectory of the asteroid, this comet represented something far more volatile, far more mysterious, and in its own way, far more profound. Its discovery was a testament to the elegant, often accidental, nature of modern astronomy. The comet was first spotted on September 11th by an instrument that wasn't even looking for it. Aboard the SOHO spacecraft, a joint NASA and ESA mission that has been staring at our sun for decades, is an instrument called SWAN, which stands for Solar Wind Anisotropies. SWAN's primary mission has nothing to do with comets. Its job is to map the invisible flow of hydrogen atoms that stream out from the sun, the solar wind, as it interacts with the interstellar medium at the very edge of our solar system. But it turns out that this constant, patient hydrogen mapping has a wonderful side effect. Comets, in their simplest form, are dirty snowballs. And when these frozen relics from the dawn of time begin their final sunward plunge, the increasing heat causes their ices to sublimate, to turn directly from solid to gas. Chief among these gases is hydrogen-rich water vapor, which erupts from the comet's nucleus in vast, invisible quantities. SWAN, from its vantage point millions of kilometers away, doesn't see the comet itself. It sees the comet's breath. It stumbles across these new visitors by watching for their sudden, ghostly hydrogen signatures erupting against the quiet background of interplanetary space. It was a discovery born of looking for something else entirely, a whisper of hydrogen that betrayed the presence of a silent wanderer. By mid-September, the whisper had grown into a shout. Comet C 2025 R2 had brightened to approximately 6th magnitude, hovering right at the delicate threshold of naked eye visibility. For those lucky enough to be under dark, rural skies, far from the light-polluted haze of cities, it was a new star in the heavens. Amateur astronomers, the passionate sentinels of the night, began reporting sightings. Their online forums, usually filled with technical discussions of equipment and astrophotography, lit up with a different kind of energy, the pure joy of discovery. They pointed their backyard telescopes to a spot near the constellation Virgo, close to the brilliant, steady light of the star Spica and the unmistakable reddish glow of Mars, both hanging low in the western sky after sunset. Through their eyepieces, they saw it. The comet's tail, a classic signature that has inspired human imagination for millennia, was growing longer and more structured with each passing night. The relentless solar heating was driving the volatile ices to sublimate from its nucleus, creating the glowing cloud of the coma and a shimmering tail of dust and gas that stretched across the evening sky. It was a cosmic brushstroke, a transient masterpiece painted with light and ice. But comets are notoriously fragile creatures. Unlike the solid rock and metal construction of asteroids, which are built to endure the ages, comets are essentially celestial phantoms. They are loose aggregations of ice, dust, and organic compounds, held together by the weakest of gravitational forces and the frozen volatiles that bind them. They are pristine samples of the primordial solar system, preserved in the deep freeze of space for billions of years. But as they approach the sun, the very same heating that creates their spectacular, Life-giving tails can also be their undoing. The process can tear them apart entirely. Many of the comets discovered by the SWAN instrument, these fresh visitors from the far-flung Oort cloud, never survived their first violent encounter with solar radiation. They fragment into streams of debris, producing brief, beautiful meteor showers for us on Earth before dissipating completely, their ancient story scattered into dust. The physics behind this celestial life and death struggle involves a complex interplay of sublimation temperatures and solar heating. Water ice, the primary component of most comets we know, begins to vigorously sublimate at temperatures around -73°C, 200 Kelvin. But other, more volatile compounds, like frozen carbon dioxide and methane, begin to outgas at even greater distances from the Sun, where the cold is far more profound. As these materials transition directly from solid to vapor, they don't just gently float away. They erupt from the nucleus in powerful jets of gas. These jets act like tiny, unpredictable rocket engines, and they can dramatically alter a comet's trajectory through what are known as non-gravitational forces. This is what makes comet orbits notoriously difficult to predict with high precision, especially for objects like C-2025R2, which may be making their very first approach from the distant, mysterious Oort cloud, a journey that has taken thousands or even millions of years. Throughout September, the survival prospects of Comet C-2025R2 remained utterly uncertain. As a fresh comet from the outer solar system, it likely contained pristine ices that had never before been exposed to significant solar heating. When these ancient materials finally encounter the sun's radiation for the first time, their rapid, violent sublimation can create immense internal stresses that exceed the comet's fragile structural integrity. The nucleus might split into multiple fragments, each one growing its own ghostly tail and coma. Or it might disintegrate entirely, dissolving into an expanding, invisible cloud of debris. The astronomers and skygazers watching from Earth could only hold their breath and wait, knowing that the beautiful ghost in their telescopes could vanish at any moment. Yet, even as this new, fragile comet commanded the attention of amateur observers, another, very different kind of cosmic celebrity was preparing for its own moment in the spotlight. Asteroid 99942 Apophis, the 400-meter-wide mountain of rock that once gave planetary defense experts nightmares, was continuing its inexorable, gravitationally bound approach toward what will be the closest asteroid encounter in recorded human history. On April 13, 2029, Apophis will not be a faint smudge in a telescope. It will sweep past Earth at a distance of just 32,000 kilometers, closer than our geostationary communication satellites. It will appear as a bright, fast-moving star, visible to the naked eye, even from the light-drenched skies of major cities. Observers will be able to watch its motion against the starfield in real time, a terrifyingly swift and silent passage at 50,000 kilometers per hour. The presence of this known, calculated, future threat added a strange counterpoint to the unfolding events of September 2025. It was a reminder that our solar system contains not just beautiful, transient wonders, but also long-term, predictable dangers. The clustering of these significant encounters, the asteroid swarm, the brightening comet, and the looming approach of Apophis all, within such a short window of time, seemed to challenge the simple notion of a purely random distribution of cosmic events. Part of this apparent increase, of course, was still due to observational bias. The completion of major asteroid surveys over the past 2 decades had dramatically improved our ability to detect and track these objects. The Vera C. Rubin Observatory was now poised to represent another quantum leap in that capability. But better eyes alone didn't seem to fully explain the sheer diversity of the objects involved. We had the asteroids, rocky and metallic remnants of planetary formation. And now we had the comet, a volatile-rich object whose behavior could be wild and unpredictable. These different types of small bodies reflect the complex history of our solar system's birth and evolution. But they also present entirely different challenges for planetary defense. Tracking an asteroid is one thing. Predicting the path of a jet-spewing, self-propelled dirty snowball is another entirely. As autumn of 2025 progressed, the cosmic stage was set for even more remarkable revelations. The September surge of these familiar, if unusually active, solar system objects was about to be completely overshadowed by something unprecedented. A visitor from another star system entirely. An alien messenger carrying chemical signatures that would challenge our most fundamental assumptions about how planets are born. But first, this mysterious traveler would have to navigate the complex gravitational environment of our inner solar system, all while remaining hidden behind the blinding glare of the sun during its most critical and dangerous passage. When it finally emerged into our telescopic view in early December, 3.1 Atlas would prove to be unlike anything astronomers had ever seen before. On July 1, 2025, a routine, automated sky survey captured something extraordinary, disguised as the most unremarkable thing in the universe, a single faint dot of light. High in the crystalline air of the Chilean Andes, the Atlas telescope array at Rio Ardo had spent the night doing what it always does, methodically photographing the sky its digital eyes, tirelessly watching for anything that moved against the stellar background. On any given night, it would photograph thousands of such objects known asteroids on their predictable paths, distant comets making their slow pilgrimage, and the occasional fleeting flash of a dying star. The automated systems, the silent, thinking heart of the observatory, flagged this particular dot for follow-up observations based on its apparent motion, just as it had flagged countless others before. It was initially catalogued as just another potential near-Earth object, another piece of anonymous cosmic shrapnel to be tracked, assessed, and likely forgotten. There was no fanfare, no sudden gasp of discovery. There was only the quiet, rhythmic hum of machines doing their job. But this particular dot of light would soon rewrite our understanding of what travels between the stars. Within days, as per standard procedure, the alert went out. Telescopes around the world, from the volcanic peaks of Hawaii to the arid plains of Australia, swiveled their massive structures to get a look. This is the routine, meticulous process of astrometric follow-up, the global detective work of modern astronomy. Each new observation, each new data point, refines an object's trajectory with increasing precision. And it was during this routine, almost mundane, process that astronomers began to realize they were dealing with something utterly unprecedented. The mathematics, cold and pure and stripped of all emotion, began to tell a story that was anything but mundane. As more and more data refined the object's orbital elements, one parameter began to stand out with startling, impossible clarity. Its orbital eccentricity exceeded unity. In the precise language of celestial mechanics, this is the irrefutable signature of a hyperbolic trajectory. For the rest of us, it was the astronomical equivalent of a smoking gun. An object with an eccentricity of less than 1 is on an elliptical orbit. It is a prisoner of the sun's gravity, bound to our solar system forever. But an eccentricity greater than 1 means the object carries more than enough velocity to escape the sun as gravitational influence entirely. It meant this object wasn't from around here. It wasn't a long-lost cousin from the Oort cloud or a stray from the Kuiper belt. This object wasn't bound to our solar system. It was just passing through. It was a tourist with a one-way ticket, and its journey had begun in the unimaginable depths of interstellar space. The dot of light was given a new, momentous designation, 3I A2LAS. The 3I stood for the third interstellar object ever confirmed in human history. It followed in the ghostly footsteps of 1I Oumuamua, the bizarre, cigar-shaped object that had tumbled through our system in 2017, and 2I Borisov, a more recognizably comet-like visitor that arrived in 2019. But unlike those previous, fleeting visitors, 3I Atlas arrived with what seemed like a generous, almost deliberate sense of timing. Its trajectory was a gift. It was calculated to carry it to perihelion, its closest and most violent encounter with the Sun, on approximately October 30th, 2025. This would be followed by its closest approach to Earth in mid-December, at a vast but manageable distance of roughly 1.8 astronomical units. That translates to approximately 270 million kilometers, far enough to pose absolutely zero threat to our world, but close enough for our most powerful telescopes to perform a detailed forensic analysis. It was as if the cosmos had arranged for a special delivery service, dropping off a pristine, untouched sample from another star system with optimal viewing conditions and plenty of advanced notice. But the object's incredible trajectory was only the beginning of its mysteries. As the observational data accumulated throughout the long, warm summer and into the early autumn of 2025, 31ATLAS began to display characteristics that challenged our fundamental assumptions about both interstellar space and the behavior of comets. First came the size estimates. Observations from the Hubble Space Telescope, our venerable eye in orbit, suggested an upper limit of approximately 5.6 kilometers for the nucleus, though its actual size was likely much smaller. This placed it in an interesting intermediate range, larger than many typical comets, but smaller than a significant asteroid. What truly set 3I ATLAS apart from its interstellar predecessors, however, was its unmistakably cometary behavior. Unlike Oumuamua, which had shown no visible coma or tail, despite its puzzling acceleration away from the Sun, 31ATLAS began to perform exactly as a comet should. As it fell inward, it developed a classic cometary appearance. By September, ground-based telescopes were resolving a substantial coma, the glowing, ethereal cloud of dust and gas surrounding the nucleus, along with the beginnings of what would become an impressive structured tail. This cometary activity, this outgassing of ancient materials, was more than just a beautiful spectacle. It was the first clue that we were about to encounter a truly alien chemistry. It was the moment the interstellar messenger began to open its mouth to speak. And when it did, the James Webb Space Telescope was there to listen. In the late summer, the most powerful infrared observatory ever built turned its golden mirrors toward 3I ATLAS. The results that came back were, in a word, stunning. The light from the comet's coma, broken down into its constituent chemical fingerprints by JWST's spectrographs, revealed a recipe unlike anything ever seen in a comet from our own solar system. The object's coma showed an unusually, almost impossibly, high ratio of carbon dioxide to water vapor. It was among the highest CO2 to H2O ratios ever measured in any comet, from any place, at any time. To understand why this chemistry is so profoundly significant, you have to understand how comets are typically born. In the swirling disk of gas and dust that forms a planetary system, protoplanetary nebula-different materials condense at different temperatures. Water ice, the stuff of our own comets, freezes out at about minus 123 Celsius, 150 Kelvin. This corresponds to a region in our solar system, roughly between the orbits of Mars and Jupiter, a boundary known as the snow line. Carbon dioxide, however, has a much lower freezing point. It only condenses into ice much farther out, beyond the orbit of Neptune, where the Sun is a distant star and temperatures plummet below minus 195 Celsius, 78 Kelvin. The extreme dominance of carbon dioxide in 3I Atlas suggested it had been born in the truly frigid outer regions of its parent planetary system, far beyond where most of our own comets originate. Either this object had condensed from a protoplanetary disk that was, for some unknown reason, unusually rich in carbon dioxide, or it had formed so incredibly far from its parent star that water ice never had a chance to accumulate in significant quantities. It was a clue that pointed to a birthplace unimaginably different from our own. But the chemical anomalies didn't stop there. As JWST was uncovering the CO2 mystery, another giant eye, the Very Large Telescope in Chile, was finding its own puzzle. Spectroscopic observations from the VLT revealed another strange feature: prominent emission lines from nickel atoms, with surprisingly weak corresponding signatures from iron. This was another flagrant violation of the local cosmic rules. In typical solar system comets, and indeed in our sun and planets, iron and nickel occur in roughly fixed solar proportions, a reflection of the elemental composition of the stellar nebula from which they all condensed. The apparent depletion of iron relative to nickel in 3I Atlas hinted at chemical processing or formation conditions utterly alien to our local cosmic neighborhood. It was as if we had found a rock on Earth with no silicon in it. It simply shouldn't be that way. As autumn progressed and 3I Atlas continued its inexorable sunward plunge, its visual appearance became ever more complex and spectacular. The Gemini Observatory and other world-class facilities documented multiple, distinct tail components, with different orientations, colors, and compositions. It wasn't a single, simple tail, but a complex, evolving structure, suggesting that different volatile materials were erupting from different regions of the nucleus as it slowly tumbled through space. After a journey that may have lasted for billions of years in the cold, silent emptiness between the stars, the object was literally coming alive under the heat of our sun. And as it awakened, it was revealing secrets that threatened to overturn decades of astronomical theory. The question was no longer if this visitor would provide new insights into the cosmos. The question was whether we were prepared for the profound implications of what it had come to reveal. For the astronomers tasked with deciphering the story of 3I Atlas, the timeline of its passage through our inner solar system presented both a golden opportunity and a maddening challenge. The comet was a celestial treasure chest, and it was slowly beginning to open. But just as it was about to reveal its most precious contents, it would be snatched away, hidden from view by the very star that was forcing it to give up its secrets. As it raced toward its late October perihelion, its closest approach to the sun, the comet would become increasingly, and then impossibly, difficult to observe from Earth. Its path across our sky was bringing it into ever closer alignment with the sun itself. From our terrestrial vantage point, it was like watching a ship sail directly behind a lighthouse beacon. The glare would simply become too overwhelming. This period of forced observational blindness was a source of immense frustration for the scientific community. The weeks surrounding perihelion were, without question, the most scientifically valuable phase of the entire encounter. This was when the object would be subjected to maximum solar heating. This was the moment of trial by fire. The intense radiation would sublimate not just the highly volatile carbon dioxide, but also the more stubborn ices, potentially exposing and releasing materials from deep within the nucleus, materials that had been locked away and preserved in a pristine state since the object S formation billions of years ago. Chemical species that had remained locked in solid form during the long, cold interstellar journey would finally be liberated into the vapor phase, revealing their unique spectroscopic fingerprints to any telescope capable of detecting them. This was the moment of truth, the point at which the comet's deepest, most ancient secrets would be laid bare. But the same solar radiation that promised to unlock this interstellar time capsule would also render it effectively invisible. The object's trajectory was calculated to carry it to within approximately 0.44 astronomical units of the sun, that is a scorching 60 million kilometers, closer than the orbit of Mercury. From Earth's perspective, this placed 3I Atlas less than 10 degrees from the solar disk, burying it completely in the twilight glow and the scattered light of our atmosphere, a region where precision astronomy is simply impossible. The enforced observational hiatus created a tantalizing, almost unbearable mystery, a cliffhanger on a cosmic scale. The central question was one of survival. Would 3I Atlas emerge from its passage through the solar furnace in December as a single, coherent object, perhaps with its activity even enhanced by the fresh exposure of volatile ices? Or would the intense thermal stresses, the dramatic temperature gradients between its sun-baked surface and its frozen core, prove to be too much? Would its internal structure fracture, breaking it apart into multiple fragments that would then create an expanding debris cloud, a ghostly procession of smaller, independent cometary objects? This survival question carried implications that reached far beyond mere academic curiosity. If it survived intact, it would suggest that interstellar objects possess a surprising degree of structural integrity, a robustness that allows them to preserve their ancient chemical signatures, even when subjected to the intense thermal processing of a close solar pass. This would be a crucial piece of data, telling us that these messengers can, and do, deliver their information reliably. Fragmentation, on the other hand, while spectacularly photogenic, might be a scientific disaster. It could disperse the very materials that made 3I Atlas so scientifically valuable, transforming a single pristine sample from another star system into a diffuse, confusing collection of processed debris streams. Historical precedent offered little guidance. Most of the solar system comets that we see fragment during close solar approaches are these: fresh visitors from the Oort cloud, objects making their very first encounter with significant solar radiation after eons in the deep freeze. 31A-TLAS, by contrast, was a battle-tested survivor. It had already demonstrated remarkable structural stability simply by enduring its billion-year journey through interstellar space, a voyage that would have subjected it to cosmic ray bombardment, thermal cycling, and countless other stresses. Was it a fragile snowball or a hardened cosmic voyager? We were about to find out, but we wouldn't be able to watch. The cosmic irony was palpable. After traveling unimaginable distances across space and time to reach our solar system, 31A-TLAS would spend its most active and revealing moments hidden behind the very star that was driving its spectacular transformation. It was like attending a concert where the featured performer disappears behind a curtain just as they begin their most important song. The global astronomical community could do nothing but wait, their powerful instruments pointed elsewhere, while the most dramatic act of the celestial performance played out in the unseen glare. But astronomical patience, born of staring into the vast, slow-moving clockwork of the cosmos, has its rewards. Earth's own orbital motion around the sun is a predictable, reliable engine of changing perspectives. As we continued on our own journey, the viewing geometry would gradually, inexorably, improve. Throughout November, the angular separation between 3I-ATLAS and the sun would begin to increase. And by early December, it would finally start to emerge from the solar glare, a celestial phoenix rising into the pristine, dark skies of a pre-dawn Earth. The object's closest approach to our planet was calculated from mid-December. At a distance of approximately 270 million kilometers, it might seem vast by terrestrial standards, but for astronomers, it represented near-perfect conditions for a detailed forensic study. It would be close enough for our major telescopes to collect substantial amounts of light, allowing for high-resolution spectroscopy that could tease out even the faintest chemical signatures. It would be far enough to avoid any atmospheric interference from Earth's own thermal radiation. And it would be positioned high in the pre-dawn sky, a time when the background contamination from scattered light is at its absolute minimum. The December observing window was set to be the best opportunity to study intact interstellar material that human science might encounter for decades, or perhaps even centuries. Unlike the brief, fleeting visit of Oumuamua, 31A-TLAS's trajectory and timing would keep it well within range of our major observatories well into 2026, providing months of sustained observation across multiple wavelength ranges, from radio to X-ray. It was a long, slow, deliberate examination, not a fleeting glimpse. Meanwhile, the other members of the September cosmic cast were preparing for their own observational moments. Comet C 2025 R2, the swan discovery that had been brightening so beautifully throughout the autumn, was now facing its own survival challenge as it approached its own perihelion in early November. If it survived, it promised to provide spectacular naked-eye viewing for observers in the northern hemisphere throughout the winter, a beautiful lingering epilogue to the year's celestial drama. Its visibility window was narrowing as its trajectory carried it deeper into the evening twilight. But experienced comet hunters were already reporting possible naked-eye detections under dark rural skies. Binoculars revealed a distinctive greenish coma and a growing tail, classic signatures of active outgassing. Whether this beautiful display would continue or end in a sudden, catastrophic fragmentation remained to be seen. And far beyond, the silent, hulking form of asteroid 99,942 Apophis continued its inexorable approach. While its 2029 encounter was still 3.5 years away, our ground-based telescopes were already beginning their extended characterization campaigns. These were long-term projects designed to meticulously map the asteroid's surface properties, determine its precise rotation state, and probe its internal structure before the close flyby with Earth irrevocably altered these very characteristics. Out in the void, NASA's OSIRIS-APEX spacecraft, a repurposed version of the successful OSIRIS-REx sample return vehicle, was on its multi-year cruise phase, conducting periodic check-ins and navigation adjustments. It was on a direct course to rendezvous with Apophis shortly after the 2029 Earth encounter, ready to provide close-up, detailed observations of how the powerful gravitational interaction with our planet had physically reshaped the asteroid. It was a natural experiment on a planetary scale, and we had a robotic probe on its way to witness the aftermath. But the most dramatic enhancement to our cosmic surveillance capabilities was still just ramping up its operations. The Vera C. Rubin Observatory's first light images had been a stunning proof of concept, but the facility was still in its commissioning phase during the autumn of 2025. Once it became fully operational, it would rescan the entire accessible sky every few nights, providing a near real-time monitoring of the cosmic traffic in our local neighborhood. This enhanced cadence, this relentless, sweeping gaze, would revolutionize asteroid detection and tracking. It might even prove, once and for all, that the September surge was not an anomalous clustering of events, but rather a representative sample of the true, busy, and slightly chaotic activity level in near-Earth space. The drama of 2025, it was becoming clear, was not just about the objects themselves. It was about our own awakening to the universe we have always inhabited, but never truly seen. In an age of instant information and global connectivity, where a single, startling image can circle the globe in minutes, it was perhaps inevitable. In a world where the line between hard data and speculative fiction can blur with the click of a mouse, it was a question that was bound to be asked. As the autumn of 2025 deepened, as the data on 3i Atlas grew more detailed and its behavior more perplexing, the whispers began. They started quietly in the esoteric corners of the internet, on late-night talk shows, and in hushed, speculative conversations. But soon the whispers grew louder, coalescing into a question that has haunted every unusual astronomical discovery since the dawn of the space age. Could this be evidence of extraterrestrial intelligence? The object's unprecedented chemistry, a recipe that seemed to violate the known rules of planetary formation. Its complex, evolving behavior, with its multiple tails and episodic brightenings. And above all, its remarkably convenient timing, an arrival that seemed perfectly choreographed for observation by our most advanced telescopes. By late September, this confluence of anomalies had conspiracy theorists and a small but vocal minority of serious researchers working overtime. Was 3i ETLS merely a natural wonder, an exotic but ultimately understandable piece of cosmic debris? Or was it something more? Was it an artifact? A probe? A message in a bottle, tossed into the galactic ocean from a shore we cannot see? The speculation began, as it often does, not with wild-eyed pronouncements, but in the more sober and measured environment of academic circles. Researchers, in their papers and conference discussions, began to note the striking similarities between 31ATLAS and the controversial object that had preceded it, 1I Oumuamua. That 2017 visitor had sparked a fierce and still simmering debate about its possible artificial origins. Both were interstellar travelers. Both displayed unusual properties that challenged our conventional understanding of cosmic objects. And both, with an almost theatrical flair, had arrived on trajectories that provided excellent, though fleeting, observing opportunities for human astronomers. It felt, to some, like a pattern was emerging. But for all the superficial similarities, the differences between the two visitors were profound and, for most scientists, incredibly telling. The case for Oumuamua's artificial nature had rested on its enigmatic properties, its highly unusual, elongated shape inferred from its light curve, and its mysterious non-gravitational acceleration. It was speeding up as it left the solar system, pushed by a force that wasn't gravity. Yet it showed no visible signs of cometary, outgassing no coma, no tail that would explain such a push. It was a ghost in the machine of celestial mechanics, a puzzle that still lacks a universally accepted solution. 31ATLAS, on the other hand, was behaving exactly like what it appeared to be, a comet. A very, very strange comet, to be sure, but a comet nonetheless. It developed a classic beautiful coma and tail structure as it approached the sun. Its brightness variations, including the sudden outbursts, followed predictable patterns based on the physics of volatile sublimation, even if the volatiles themselves were exotic. Its trajectory, while hyperbolic, showed the expected gravitational deflection from its interaction with the sun, with any additional minor perturbations easily and precisely explained by the gentle rocket-like push of its outgassing jets. Most importantly, and most decisively for the vast majority of astronomers, 3.1 Atlas exhibited absolutely no signs of controlled or directed motion. There were no sudden course corrections, no unexplained changes in velocity. Its path through our solar system was a perfect, elegant testament to the power of gravity, following the precise hyperbolic trajectory expected for an unbound visitor under the influence of the sun and nothing else. There were no radio transmissions, no geometric shapes or artificial structures visible, even under the highest resolution observations available to human telescopes. It was a wild, natural thing, not a machine. The scientific method, at its core, is a discipline of skepticism. It demands that extraordinary claims be supported by extraordinary evidence. And the evidence for 3IATLA, every single bit of it, consistently pointed toward natural phenomena. They were phenomena unlike anything previously observed in our cosmic neighborhood. Yes, but they were still phenomena with plausible, rational explanations rooted in the well-established physics and chemistry that govern the universe. Consider the extreme carbon dioxide dominance that made its chemistry so remarkable. While unprecedented in the comets of our own solar system, this composition could easily be the natural result of formation in the outer, colder regions of an unusual planetary system. A system born around a star with a different mass, a different chemical makeup, or a different planetary architecture might naturally produce comets with chemical signatures that would seem utterly alien to observers like us, familiar only with the local products of our own sun's nebula. The apparent depletion of iron relative to nickel, while deeply puzzling, could also have natural explanations. It could reflect formation in a stellar environment with non-solar elemental ratios, perhaps around an ancient star from the galaxy's thick disk. Or it could be the result of subsequent processing during its unimaginably long journey through interstellar space. Billions of years of relentless bombardment by high-energy cosmic rays, slow-motion impacts with interstellar dust, and thermal cycling in the near-absolute zero temperatures of the void could selectively alter its surface composition, creating unusual spectroscopic signatures without requiring any kind of artificial intervention. Even the complex multi-component tail structure and the episodic brightening events, while spectacular, had precedents, albeit less extreme ones, in the comets of our own solar system. The magnificent comet Hale-Bopp in the late 1990s displayed multiple tails with different compositions. Comet Holmes in 2007 underwent a dramatic, inexplicable outburst that caused its brightness to increase by a factor of nearly 1,000,000 in just a few hours. Nature, it was clear, was perfectly capable of producing the kinds of spectacular and unusual behaviors that were being observed in 3I ATLA. The real question, then, wasn't whether 3I Atlas could be artificial. The more interesting question was why so many people wanted it to be. Part of the answer, perhaps, lies in the profound psychological impact of contemplating truly interstellar scales. When we observe an object that has journeyed from another star system, we are confronting, in a very direct and physical way, the possibility that we are not alone. The human mind, which evolved to navigate complex social hierarchies and to detect agency and intention in the world around us, naturally looks for signs of purpose in unexplained phenomena. This tendency becomes even stronger when we are dealing with objects that seem to violate our expectations or display properties that stretch the limits of our conventional explanations. 31ATL's unusual chemistry and its convenient observing geometry triggered the same ancient pattern recognition systems that our ancestors used to identify a potential predator in the rustling grass or a potential ally in a stranger's face. When faced with something so unprecedented, the brain's default assumption, honed by millions of years of evolution, is often that someone or something must be responsible. But nature routinely and beautifully produces phenomena that exceed the limits of human imagination. The universe has had 13.8 billion years to experiment with physics and chemistry under conditions that range from the unimaginable pressures inside massive stars to the near absolute zero temperatures of interstellar space. The fact that we, in our infinitesimally brief moment of scientific awareness, occasionally encounter natural processes or objects that surprise us is not evidence of artificial origin. It is evidence that our understanding of the cosmos remains fundamentally and wonderfully incomplete. It is a sign not of alien intelligence, but of our own cosmic infancy. And as 3I Atlas raced towards its hidden rendezvous with the sun, it was carrying a lesson for us, not about who else might be out there, but about the staggering, creative, and endlessly surprising power of the universe itself. The media landscape surrounding any major astronomical discovery tends to act as a powerful amplifier. In the case of 3I Atlas was no exception. It is a simple, immutable law of public interest. A headline reading, "Scientists baffled by mysterious interstellar visitor," will always generate more clicks, more shares, and more breathless commentary than one that reads, "Researchers study unusual but natural comet," regardless of which statement more accurately reflects the scientific consensus. This creates a powerful feedback loop. Public interest, piqued by the hint of the unknown, drives sensationalized coverage, which in turn feeds more speculation about exotic and often artificial explanations. The careful, methodical process of science, the slow accumulation of data, the cautious proposing and testing of hypotheses, is often drowned out by the much louder, more exciting narrative of an alien encounter. Social media, with its frictionless, instantaneous spread of information, compounds this effect 1,000-fold. It allows unfiltered speculation to achieve a kind of viral velocity, outpacing the more deliberate, peer-reviewed pace of careful scientific analysis. By the time astronomers have collected sufficient data to truly characterize an object as properties and confidently rule out artificial origins, the alternative theories, unburdened by the need for evidence, have already achieved a life of their own. They become embedded in the public consciousness, stubbornly resistant to correction by mere factual information. The historical pattern is as clear as it is consistent. Every truly unusual astronomical discovery, from the first detection of pulsars in the 1960s, briefly labeled LGM-1 for little green men, to the enigmatic fast radio bursts of today, has initially faced a wave of speculation about possible artificial origins. And in every single case, without exception, continued observation and deeper analysis have revealed natural explanations that, while often more complex and fascinating than initially anticipated, require no involvement from extraterrestrial intelligence. This doesn't mean we should ever abandon the search for evidence of extraterrestrial technology. The universe is a place of staggering size and unimaginable age. It seems not just possible, but statistically probable, that it contains other intelligent civilizations, some of which might be capable of interstellar travel or communication. But the detection of such a civilization will not be a matter of ambiguity or interpretation. It will require clear, unambiguous evidence of artifice. It will be a coherent radio signal carrying complex, information-rich content. It will be an object displaying controlled, non-ballistic motion that is inconsistent with the natural forces of gravity and radiation pressure. It will be a structure whose geometry or thermodynamics violates the laws of physics as we understand them. 3.1 Atlas displayed none of these characteristics. Its radio emissions, where they could be detected at all, consisted entirely of the natural thermal radiation expected from a cold body and the faint, predictable molecular line emissions typical of cometary outgassing. Its trajectory, while extraordinary, followed the predictable mechanics of gravity, with any minor perturbations easily and fully explained by the gentle, chaotic thrust of its sublimating ices. Its internal structure, as revealed by thermal modeling and photometric observations of its rotation, was consistent with a loose, porous aggregate of ice and rock, a rubble pile held together by the weak forces of gravity and cohesion. It was, in short, behaving exactly like a natural object. Perhaps most tellingly, 3I ATLAS was behaving in a way that was not just natural, but in a way that was expected. Our theoretical models of how planetary systems form and evolve have long predicted that every star system should be a messy, chaotic place in its youth. As giant planets migrate and gravitational resonances shift, these systems should eject a significant quantity of their small bodies, their comets and asteroids, into the vast emptiness of interstellar space. For every kilogram of material that remains gravitationally bound in planets and asteroid belts, perhaps 10 times that amount gets flung out into the galaxy by powerful gravitational slingshot effects. These calculations predict that the galaxy should be teeming with these wandering fragments from billions of stellar nurseries, a vast, invisible diaspora of planetary construction debris drifting silently between the stars. The chemistry and physical properties of these interstellar nomads should, by rights, reflect the conditions in their parent systems. A system born around a massive, hot star should produce different debris than one born around a small, cool red dwarf. A system rich in heavy elements should produce different debris than one that is metal poor. An authentic sample of another star system's debris should look alien compared to the objects in our own solar system. It should still obey the same fundamental laws of physics and chemistry that govern all matter throughout the universe. But its specific recipe, its elemental ratios and isotopic signatures should be different. In other words, 3I-ATLA looked exactly like what it claimed to be. It was a natural product of planetary system formation around another unknown star, carrying the chemical fingerprints that reflected formation conditions very different from those that produce our local solar system family. The very fact that it seemed so strange to human observers was not evidence of its artificial origin, but rather a powerful confirmation that we live in a galaxy where the conditions for planetary formation vary dramatically from system to system. It was a messenger, not from an alien intelligence, but from the beautiful, creative, and endlessly diverse processes of nature itself. As 3I Atlas continued its final approach toward its fiery perihelion, the accumulated evidence was a chorus singing the same song: natural, natural, natural. But this conclusion, while closing the door on one sensational possibility, opened a window onto an even more intriguing and perhaps more profound question. If this was not an artifact, but a fossil, then what was its story? Where, exactly, had this ancient wanderer spent the billions of years between its violent ejection from whatever star system created it and its recent, spectacular arrival in our cosmic neighborhood? The answer to that question would require a different kind of detective work. It would demand a sophisticated modeling of galactic dynamics, a reconstruction of stellar motions across geological timescales, a journey backward not just through space, but through the deep, almost unfathomable currents of time. And the preliminary attempts to trace 31ATLA's trajectory backward to unwind its long and lonely journey were already beginning to yield tantalizing clues about the object's ancient origins and the remarkable story that had brought it to our telescopes at precisely the right moment for us to read its pages. To trace the biography of an interstellar visitor is to become a cosmic archaeologist. It is an attempt to reconstruct a journey that may have lasted longer than the Earth itself has existed. The object known as 3I Atla was not just a comet. It was a time capsule, locked within its alien chemistry and encoded in its extraordinary trajectory was the fossilized record of cosmic events that had unfolded billions of years ago in an era when our galaxy was younger, wilder, and the distribution of stars and the heavy elements they forged was dramatically different from the more sedate, middle-aged configuration we see today. The first clues to the object's ancient origins, the first faint whispers of its long story, began to emerge from a discipline known as kinematic analysis. This is the painstaking, computer-intensive work of mathematical modeling that attempts to trace an object's motion backward through space and time. It is like trying to reconstruct the path of a single, wind-blown seed back to the specific tree in a specific forest from which it fell 1,000 years ago. The task is complicated by the fact that the forest itself is constantly moving. The stars of the Milky Way are not fixed points of light. They are a swirling, dynamic river of suns, each on its own vast, gravitational orbit around the galactic center. To trace the path of 3I Atlas, you have to account for this celestial dance. You have to rewind the clock on the galaxy itself. Preliminary calculations, run on supercomputers by researchers at the European Southern Observatory, began to point to a remarkable possibility. When they traced the object's path backward, accounting for the gravitational pull of all the known stars, it would have passed its trajectory seemed to originate not from the plane of the galaxy where our sun resides, the so-called thin disk, but from a more diffuse older population of stars known as the galactic thick disk. This was a stunning revelation. The thick disk is a population of stars that formed during the Milky Way's chaotic early evolution, a period between roughly 7 and 12 billion years ago. If these kinematic models proved to be correct, it would mean that 3I Atlas was older than our entire solar system. It would mean that this small, icy wanderer had already been drifting through the silent, cold expanse of interstellar space since before the sun itself had condensed from its parent molecular cloud. It would mean that the chemical signatures preserved in its ices were a direct sample from an era when star formation rates were dramatically higher, and the galaxy's heavy element content, the very stuff from which planets are made, was substantially different from today's values. It was not just a visitor from another star. It was a visitor from another, more ancient, epoch of the galaxy's history. This thick disk hypothesis gained immediate and powerful support from the object's strange and unusual chemistry. We know that stars in this ancient galactic component typically show different elemental abundance patterns compared to younger, thin disk populations like our sun. the apparent depletion of iron, and the extreme dominance of carbon dioxide that had been observed in 3Ia TLAS, which were so alien to our local experience, might be perfectly normal for an object formed around an ancient thick disk star, a star born with a different non-solar metallicity and a correspondingly unusual mix of volatile chemicals in its protoplanetary disk. The chemistry and the trajectory were telling the same story. But how does a small, fragile body like a comet escape from its parent stellar system to begin such an unimaginably long journey? The ejection process is a violent one, a gravitational drama that typically unfolds during the chaotic, early phases of planetary system evolution. As massive, Jupiter-like worlds migrate inward or outward, their orbits shifting due to complex interactions with the primordial disk of gas and dust. They act as powerful gravitational slingshots. They can scatter the smaller objects in their path, comets and asteroids, like a celestial bat hitting a shower of baseballs, flinging them onto hyperbolic, escape velocity trajectories that carry them out of the system entirely. Our computer simulations of planet formation suggest that this is a common and incredibly inefficient process. For every kilogram of material that successfully remains gravitationally bound in planets, asteroids, and comets, perhaps 10 kilograms or more, gets unceremoniously flung into the dark emptiness of interstellar space. This means the galaxy should be populated with trillions upon trillions of these wandering fragments from billions of stellar nurseries of vast, silent diaspora of planetary construction debris. Once ejected from its parent system, 3I Atlas would have begun its solitary odyssey. It would have journeyed through the near-perfect vacuum of interstellar space, an environment where the typical density of matter is roughly one single atom per cubic centimeter, a better, more profound vacuum than anything achievable in our most advanced terrestrial laboratories. In this environment, the object would have been essentially isolated from external influences, perfectly preserved in a cosmic deep freeze at temperatures hovering just a few degrees above absolute zero. Its internal clock would have effectively stopped. Yet this interstellar journey was not entirely uneventful. It was a voyage of incredible loneliness, but not one of complete isolation. Recent, more detailed modeling by specialists in galactic dynamics has begun to identify several close encounters with other stellar systems during 3I Atlas's long and wandering voyage. Over the past 10 million years alone, a mere final leg of its journey, the object appears to have passed within 1 parsec, approximately 3 light years, of at least half a dozen different stars. Each of these encounters, while distant, would have been significant. Each one would have subtly altered its trajectory through gentle, persistent gravitational perturbations. The most significant of these recently identified stellar encounters appears to have occurred approximately 4 million years ago, when 3I ATLAS passed within roughly 1 light year of a small, dim red dwarf star in the constellation Cassiopeia. The gravitational influence of this close approach, while gentle, would have been sufficient to measurably deflect the object's trajectory. This could potentially explain why its current motion doesn't point back toward any obvious single parent system in the galaxy's thick disk. Its path has been subtly bent and reshaped by the stars it has passed along the way. This long, silent journey also raises fascinating questions about the object's surface evolution. Billions of years of relentless cosmic ray bombardment would have gradually and profoundly altered the chemistry of its exposed ice and rock surfaces. High-energy particles from distant supernova and other violent galactic phenomena would have slammed into its surface, breaking chemical bonds, creating exotic isotopic ratios, and possibly generating entirely new molecular species not found in typical, more sheltered solar system materials. The extremely cold temperatures of interstellar space would have preserved most of its volatile materials in solid form. But periodic encounters with interstellar dust clouds or the powerful radiation fields of nearby massive stars might have caused brief, episodic heating events. These events could have sublimated the very surface layers and then redeposited them in different, more stable configurations. This could be another piece of the puzzle, another potential explanation for some of the unusual chemistry that our modern telescopes were now detecting. Perhaps the most remarkable thing of all is that 3.1 Atlas has maintained its structural integrity throughout this billion-year journey. It has been subjected to thermal cycling, cosmic ray bombardment, and occasional high-velocity impacts with interstellar dust grains, and yet it has not disintegrated. This suggests either that it possesses an unusually robust construction, or that it has been continually self-repairing through sublimation and redeposition processes that gradually heal micrometeorite damage and radiation-induced structural changes. Its arrival in our solar system represents the culmination of a journey that almost defies human comprehension. It is a story of survival against unimaginable odds, across distances and timescales that dwarf our own existence. And now at the end of that long, dark road, it had finally wandered into the light of a star that had a curious technological species warming, itself by its fire, a species that had just learned how to look up and listen. Consider, for a moment, the sheer, breathtaking improbability of it all. Consider the navigational precision required not of a spacecraft, but of a blind, unguided piece of cosmic debris, for it to arrive at precisely the right time and on precisely the right trajectory for optimal observation by 21st century human telescopes. For this rendezvous to occur, the object known as 3I Atlas had to survive for billions of years in the hostile, radiation-laced environment of interstellar space. It had to navigate a subtle and complex web of gravitational influences from dozens, if not hundreds, of stellar encounters, each one gently nudging its path. And finally, it had to arrive in our solar system during the infinitesimally brief historical moment when humanity not only existed, but possessed the specific technological capability to recognize it, to track it, and to begin to understand its profound significance. The timing seemed almost too perfect to be a product of mere coincidence. A few centuries earlier, it would have been dismissed by the greatest astronomers of the age as just another faint, fuzzy star, its extraordinary nature completely invisible to their primitive instruments. A few centuries later, in a future of even more advanced technology, it might have been detected, but perhaps not with the same sense of wonder and revelation. Its arrival just another data point in a vast catalog of interstellar visitors. But it arrived now. It approached perihelion just as our most advanced space telescopes, like the James Webb, were coming online. It arrived just as our understanding of interstellar chemistry had become sophisticated enough to appreciate the beautiful strangeness of its composition. It was as if the universe had a story to tell, and it had waited until we had just learned the language to read it. The biography of 3I Atlas is more than just tell the story of a single wandering object. It illuminates the broader, grander story of galactic evolution and the cosmic recycling of planetary materials. Every heavy element locked within the object's structure, the carbon, the oxygen, the silicon, the nickel, and all the other trace metals, was forged in the nuclear furnaces of ancient, long-dead stars. These elements were then distributed through the vastness of space by the violent, creative cataclysms of supernova explosions. The very atoms that make up 3I-ATLA represent the accumulated, stellar alchemy of countless generations of stars that lived and died before our solar system, and our sun had even begun to form. In a very real and tangible sense, 3I-ATLAS serves as a messenger from the ancient galaxy. It carries physical samples of the planetary formation processes that occurred under conditions dramatically different from those that created the Earth and its celestial companions. The object's alien chemistry provides us with direct, empirical evidence of how volatile materials condense and evolve in stellar environments with different masses, different metallicities, and different dynamical histories. It is a piece of another world delivered to our doorstep, offering us a glimpse into the staggering diversity of planetary creation. But perhaps the most profound aspect of this object's biography is what it reveals about the deep fundamental interconnectedness of galactic-scale processes. This object began its existence as an unremarkable part of a planet-forming disk around another star, possibly in a completely different region of the galaxy from where we are now. Through a complex, chaotic chain of gravitational interactions, the slow, majestic dance of stellar motions, and a series of cosmic accidents, it eventually found its way to our telescopes. It carried with it, across those vast distances and timescales, precious, irretrievable information about its origins. The thick disk origin hypothesis, if it is ultimately confirmed, would make 3I-ATLA-S a true fossil from the Milky Way's youth, a time when our galaxy was more actively forming stars and the chemical composition of interstellar space was substantially different from today's values. Studying this ancient wanderer could provide unprecedented insights into galactic chemical evolution, the processes of early planetary formation, and the distribution of volatile, life-essential materials in the primordial galaxy. It would be like a paleontologist finding a perfectly preserved sample of the Earth's primordial soup. Yet for all the sophisticated modeling and the brilliant chemical analysis, fundamental questions about 3I-ATLA-S's origins remain unanswered, and may remain so forever. We cannot, with our current technology, definitively identify its parent star or the specific planetary system where it was born. The gravitational chaos of galactic evolution, the slow, relentless stirring of the stellar pot over billions of years, has erased most of the traces of its original trajectory. It has left us only with statistical hints, with probabilities that point toward its possible thick disk provenance. We can know the region, the era, but perhaps never the exact address. This uncertainty reflects the inherent, almost beautiful challenges of interstellar archaeology. Unlike terrestrial fossils, which remain conveniently embedded in datable rock layers, cosmic travelers like 3I Atlas carry no direct, unambiguous evidence of when or where they originated. Their stories must be reconstructed through a painstaking process of analyzing indirect clues, their chemical composition, their isotopic ratios, their precise trajectory, and the statistical modeling of galactic dynamics. But these limitations do not in any way diminish the significance of what this object represents. Even without knowing its exact birthplace, we can be confident that it carries authentic samples from another world, a world formed under conditions very different from those in our own solar system. Every spectroscopic observation, every single chemical analysis provides new, hard data about the diversity of planetary formation processes and the incredible range of environments where worlds can emerge around other stars. As 3I-ATLA continued its final, silent approach toward its late October perihelion, the global community of astronomers was in a state of high alert and preparation. They were mobilizing their resources for the object's temporary disappearance behind the blinding glare of the sun. The weeks immediately surrounding perihelion, that period of enforced observational blindness, would be, ironically, the most scientifically valuable period of the entire encounter. This was when the maximum solar heating would drive the highest levels of outgassing, potentially stripping away the ancient irradiated surface layers and revealing the even more pristine subsurface materials that had been preserved since the object's formation billions of years ago. But the same solar glare that would hide 3I Atlas during its most active and revealing phase also added a powerful element of suspense to the unfolding story. The question of its survival was paramount. Would this ancient, battle-tested wanderer endure its trial by fire? Or would the intense thermal stresses finally prove to be too much, shattering it into a ghostly procession of fragments, like so many comets before it? When it re-emerged into our telescopic view in December, would it still be the same object? Would it still display the same unusual chemistry and the same complex activity patterns that had made it so remarkable during its long inbound approach? The answers to these critical questions would have to wait. But in the meantime, the strange convergence of the September surge and the remarkable alien properties of 3I Atlas were beginning to raise uncomfortable, almost philosophical, possibilities about the nature of our cosmic neighborhood and humanity's true place within it. Were we truly just witnessing a random, statistical convergence of unrelated phenomena? Or could there be deeper, unseen patterns at work? Patterns that somehow connected the interstellar visitor to the unusual, almost orchestrated, clustering of near-Earth object encounters. Some researchers were beginning to wonder whether the events of autumn 2025 represented not just a statistical coincidence, but the opening act of something much, much larger, a cosmic drama, playing out on scales that might dwarf our current understanding of celestial mechanics and the grand slow evolution of the galaxy itself. The human imagination, when confronted with phenomena that stretch beyond the boundaries of our everyday experience, tends to gravitate toward spectacular, often dramatic explanations. We are natural-born storytellers, and we seek narrative threads, connections of cause and effect, even in the silent, sprawling tapestry of the cosmos. In the case of 3IA2LAS and the September surge, this innate tendency began to manifest in a series of speculative, tantalizing, and ultimately unproven theories about possible cascade effects. The central idea, whispered in online forums and debated over late-night coffee, was that the interstellar visitor might not be a passive observer in the unfolding drama. Could it, somehow, be the trigger? Could its passage be the first domino in a chain reaction of cosmic events, a celestial catalyst that could fundamentally alter the familiar, clockwork dynamics of our solar system? The most romantic and persistent of these notions was the theory of gravitational shepherding. The idea was simple and intuitive. Could 3I ATLAS be gravitationally stirring up the local asteroid population, like a cosmic spoon mixing ingredients in a celestial soup? Could its passage be plucking at the invisible gravitational web that connects the objects in our solar system, dislodging asteroids from their stable orbits and sending them careening into the inner solar system toward us? It was a compelling image, a vision of a powerful outsider disrupting the delicate local order. But the cold, hard mathematics of celestial mechanics, the same mathematics that had revealed the object's interstellar origins, argued decisively and mercilessly against this romantic notion. Even at its maximum estimated mass of several trillion kilograms, a number that sounds enormous to human ears, 31ATLAS represents a mere gravitational minnow in the vast, deep ocean of solar system dynamics. Its influence on near-Earth objects at distances of millions upon millions of kilometers would be utterly, immeasurably negligible compared to the overwhelming, crushing gravitational dominance of the Sun and the giant planets like Jupiter. Isaac Newton's inverse square law, the bedrock of celestial mechanics for over 3 centuries, is unforgiving in its mathematical precision. Gravitational effects diminish with the square of the distance. This means that 3IATLAS's ability to influence other objects drops to essentially zero at the vast scales involved in the September encounters. To put this in a more terrestrial perspective, the gravitational tug between 3IATLAS and asteroid 2025 FA22 during their simultaneous presence in the inner solar system would be roughly equivalent to the gravitational attraction between 2 automobiles parked in neighboring cities. It is a force that exists, but one that is so vanishingly small as to be completely irrelevant. Yet, the very persistence of these gravitational shepherding theories, even in the face of such clear physical constraints, reveals something important about human psychology and our deep-seated relationship with cosmic phenomena. We instinctively, and often unconsciously, search for causal connections between simultaneous events. This tendency served our ancestors well when identifying the cause and effect relationships in their terrestrial environments. A rustle in the grass means a predator. Dark clouds mean rain. But this same powerful instinct can lead us astray when it is applied to the almost unimaginable scales of astronomical phenomena, scales that dwarf our everyday human experience. More exotic cascade scenarios began to emerge, involving possible connections between 3I Atlas and the behavior of our own sun. Could an interstellar visitor, with its own magnetic field and plasma environment, somehow trigger an increase in solar flaring or coronal mass ejections that might, in turn, affect space weather around Earth? This idea tapped into legitimate, well-founded concerns about solar-terrestrial interactions and the very real vulnerability of our modern technological civilization to violent geomagnetic storms. A powerful solar storm could, in theory, cripple our power grids, disable our satellites, and plunge us into a global pre-industrial darkness. However, the physics of solar dynamics operate on energy scales that make any interaction with a passing comet essentially irrelevant. The Sun, our star, is a thermonuclear furnace of almost incomprehensible power. It releases approximately 3.8 XYD watts of energy continuously. That is more power in a single second than human civilization has consumed throughout all of recorded history. The gravitational and electromagnetic influence of a small, 6-kilometer interstellar comet at distances exceeding 100 million kilometers would be completely and utterly overwhelmed by the much larger, more powerful internal forces that drive solar variability. The Sun's activity follows well-documented 11-year cycles related to the twisting and tangling of its own internal magnetic dynamo, not to the presence or absence of small, icy visitors in the outer reaches of the solar system. Correlations between the appearance of comets and an increase in solar events have occasionally occurred throughout history by pure statistical chance, but these coincidences represent nothing more than random noise, not a causal relationship. The meteor shower scenario presented another tempting, but ultimately unsupported speculation. Could 3I Atlas be trailing an invisible stream of debris, a river of dust and pebbles shed during its long journey, that might produce spectacular meteor displays when the Earth passes through the material? This idea gained a superficial plausibility from the well-known fact that most of our own annual meteor showers, like the Perseids in August or the Geminids in December, are the direct result of the Earth encountering the dusty debris streams left behind by comets from our own solar system. But an interstellar meteor stream faces fundamental physics problems that make it essentially undetectable, if not impossible. The debris ejected from 3I Atlas carries the same immense, hyperbolic velocity as the parent object itself. This means that any particles it sheds will also be on an escape trajectory. They will not settle into a stable, predictable orbit that could intersect with Earth's path year after year. They will make one single, high-speed pass through our solar system and then continue on their journey into the interstellar void, never to return. By the time our planet reached the region of space where 3I Atlas had passed through, any ejected material would have dispersed across volumes of space so vast that the particle density would become negligible. Moreover, the high relative velocities involved in these interstellar encounters mean that any hypothetical debris particles that did somehow manage to encounter the Earth would impact our atmosphere at incredible speeds, likely exceeding 70 kilometers per second. This is much, much faster than the typical meteors from our own solar system. Such high-velocity impacts would produce brief, brilliant flashes of light, not the prolonged, beautiful trails that characterize a normal meteor shower. And then there was the fragmentation fantasy, yet another attempt to weave a hidden, narrative connection between 3I Atlas and the September asteroid encounters. Could asteroid 2025 FA22 and the host of other near-Earth objects be, in fact, fragments of the interstellar visitor itself? Perhaps they had broken off during some previous unobserved passage through the inner solar system and were now following their own independent orbits that just happened to bring them back to our vicinity at the same time as their parent. This scenario, while intriguing, faced insurmountable problems with both orbital mechanics and chemical composition. True fragments from 3I Atlas would, like the parent object, retain their hyperbolic trajectories and their strange interstellar chemistry. The September asteroids displayed neither of these critical characteristics. Their stable elliptical orbits and their typical familiar carbonaceous or silicate compositions were a clear, unambiguous indication of a conventional, local solar system origin. There was no evidence of a shared lineage, no hint of a connection to the alien chemistry of the interstellar intruder. The dominoes, it seemed, were not falling. The spectacular theories, as compelling as they were, simply did not hold up to the rigorous, dispassionate scrutiny of science. Perhaps the most persistent and most human of all the cascade speculations involved not the laws of physics, but the actions of people. It was the theory of institutional secrecy, the idea that the world as governments and space agencies might be concealing evidence of more dramatic effects or more profound discoveries related to 3I Atlas. This theory, which flourished in the fertile ground of online forums and late-night podcasts, tapped into a deep and legitimate undercurrent of public concern about transparency in the fields of space surveillance and the potential for classified military implications of asteroid detection capabilities. If we can track a small, dark object millions of kilometers away, what else can we track? Who is watching, and what are they not telling us? However, the day-to-day reality of modern astronomical practice, a global enterprise built on a foundation of open collaboration, argues strongly against any kind of large-scale, coordinated cover-up. The global network of professional and amateur astronomers, a diverse and often fiercely independent community, operates on deeply ingrained principles of open data sharing and the rapid publication of new discoveries. Major observatories, many of which are publicly funded, publish their observation schedules and their target lists for the world to see. The orbital elements for newly discovered objects, the raw data of their paths across the sky, appear in international, publicly accessible databases, like the Minor Planet Center, within days, sometimes hours, of their confirmation. The entire incentive structure of academic astronomy also works powerfully against secrecy. A scientist's career, their reputation, their funding, and their legacy all depend on publishing significant discoveries in peer-reviewed journals and presenting their results at international conferences. The professional rewards for a groundbreaking discovery are immense. The idea of a global conspiracy to suppress information as monumental as the true nature of 3I Atlas would require the silent, willing coordination of thousands of competing researchers across dozens of countries. Given the competitive and often rivalrous nature of scientific research, this is not just improbable. It is a logistical and psychological impossibility. Someone somewhere would talk. More fundamentally, beyond the sociology of the scientific community, there was simply no credible evidence of any hidden effects or concealed discoveries related to 3I Atlas. Every aspect of the object's behavior, its strange chemistry, and its precise trajectory had been consistent with natural phenomena. It must be said that we're at the extreme, almost unbelievable end of our previously observed ranges, but natural phenomena nonetheless. The whispers of a cover-up were a ghost story without a ghost. And so, as rational analysis systematically dismissed the more spectacular cascade scenarios, one by one, a different, more profound, and genuinely thrilling what-if scenario began to emerge from the scientific community. It was a possibility that was not about secret conspiracies or imaginary gravitational waves, but about our own rapidly evolving perception of the universe. What if we were, at this very moment, entering an era of dramatically increased interstellar visitor detection? What if 3I Atlas was not a once-in-a-century anomaly, but simply the first of many? The Vera C. Rubin Observatory's unprecedented survey capabilities, combined with the soon-to-be-deployed space-based infrared telescopes, and an ever-improving network of international coordination, could be on the verge of revealing that objects like 3I Atlas are far, far more common than we had ever dared to suspect. Our previous estimates, based on a painfully small sample size of just 3 confirmed interstellar visitors, had suggested that our solar system should be visited by a detectable interstellar object perhaps once every year or so. But these estimates carried enormous, almost laughable, uncertainties. They were statistical houses of cards, built on a foundation of extremely limited observational data. But what if the true rate proves to be significantly higher? What if it is not 1 per year, but 10 or 20? If that were the case, then the late 2020s could be destined to witness a genuine revolution in our understanding of galactic-scale material exchange. We would be forced to re-evaluate our place in the cosmos. Instead of viewing these interstellar visitors as rare, exotic, cosmic curiosities, we might discover that our solar system is, in fact, constantly bathed in a gentle, almost invisible rain of debris from thousands, perhaps millions, of other planetary systems. This scenario would transform the nascent field of interstellar archaeology from a speculative science, based on the forensic analysis of individual, exotic objects, into a systematic, almost industrial survey discipline. It would become a new branch of astronomy, capable of characterizing the chemical and physical properties of planetary formation across the entire galaxy. We could begin to create a map, not of stars, but of the types of worlds that form around them. We could map the distribution of different stellar metallicities, the varying inventories of volatile, life-giving chemicals like water and carbon, and the different planetary architectures that litter the galaxy, all by simply studying the debris streams that carry these pristine, physical samples from distant worlds directly to our telescopes. Such a revelation would represent perhaps the most profound shift in our cosmic perspective since the Copernican revolution first dislodged us from the center of the universe. Instead of viewing the Earth and its solar system companions as isolated, self-contained products of purely local stellar evolution, we would finally and fully recognize ourselves as active participants in a galaxy-wide ecosystem. An ecosystem where material and the information it carries constantly flows between stellar systems across vast, unimaginable distances and timescales. Viewed from this new emerging perspective, the September surge of 2025 might represent not an anomalous, inexplicable clustering of unrelated events, but our very first, fleeting glimpse of the true, busy, and chaotic activity level in our cosmic neighborhood. It would mean that as our detection capabilities improve and our survey coverage expands, what currently appears to be a period of unusual and alarming activity might soon prove to be nothing more than business as usual. Business as usual for a galaxy containing 400 billion stars, all of them constantly and naturally exchanging debris through the slow, powerful dance of gravitational interactions and stellar encounters. But before we could fully evaluate these larger, almost philosophical implications, we had to survive the immediate, practical challenge of 3I Atlas's perihelion passage and its subsequent re-emergence from the solar glare. The object's behavior during its closest, most violent approach to the Sun would provide crucial, hard data about the survival of interstellar comets and the preservation of their ancient chemical signatures under conditions of extreme thermal processing. The stakes were higher than mere scientific curiosity. If 3I Atlas, fragmented during its hidden passage, if it shattered into a cloud of untraceable dust, we might lose the opportunity to study a pristine sample of intact interstellar material for decades or even centuries until another such visitor happened to arrive with a similarly favorable observing geometry. But if it survived, if it emerged from the glare scarred but whole, the December re-emergence could provide the most detailed, most revelatory characterization of authentic extrasolar material ever achieved by human science. The universe had sent us a message. The question now was whether it would survive the delivery. The cosmic choreography of late 2025 was building to its silent, unseen climax. As the Earth continued its own serene journey, the interstellar wanderer, 3I-ATLAS, was racing toward its date with solar destiny. October 30th marked the calculated moment of perihelion passage, the instant when this ancient traveler would sweep closest to our sun, a blistering turning point in a journey that may have begun before the Earth itself had cooled from a molten sphere. But this crucial, transformative encounter, the moment of greatest revelation, would unfold completely hidden from human eyes, masked by the overwhelming, unblinking glare of our nearest star. The curtain of fire had been drawn. For astronomers worldwide, the perihelion period represented a strange and deeply frustrating paradox. It was, without a doubt, the most scientifically valuable phase of the entire encounter, and it was the one phase they were utterly powerless to observe. This was the moment of maximum solar heating, the point of peak trial by fire. The influx of energy would be at its most intense, driving the highest levels of volatile sublimation, boiling off the surface layers that had been exposed to the harshness of interstellar space for billions of years. This process held the tantalizing promise of exposing the even more pristine, untouched subsurface materials, the very heart of the object, which had been perfectly preserved since the moment of its formation. Chemical species that had remained locked in solid, frozen form throughout the long, cold interstellar night would finally transition to the vapor phase, revealing their unique spectroscopic signatures to any telescope capable of detecting them. This was the ultimate unmasking. But the same life-giving solar radiation that promised to unlock the deepest secrets of 3I Atlas would also render it completely and utterly invisible from Earth. Object was now buried deep within the sun's corona from our perspective, a tiny mote of dust lost in the heart of a stellar furnace. The enforced observational hiatus was a period of intense, almost agonizing, anticipation for the global scientific community. It was a time for processing the data they already had, for running and rerunning their models, and for preparing their instruments for the moment the object was scheduled to re-emerge. And in that waiting, a single, dominant question hung in the air. Would 3I-ATLAS survive? Would it emerge in December, scarred but intact, a single coherent object whose activity had been supercharged by the fresh exposure of its volatile heart? Or would the intense thermal stresses, the violent, internal battle between its sun-scorched exterior and its cryogenically frozen core prove to be too much for its fragile structure? Would it fracture, breaking apart into a ghostly procession of multiple fragments, an expanding debris cloud of smaller, independent cometary objects? Historical precedent, based on the comets of our own solar system, offered little in the way of firm guidance. We had seen both outcomes before. Some comets, like the great comet ISON in 2013, had disintegrated completely, their long journey ending in a final, fiery dissolution. Others, like the spectacular comet Hale-Bopp, had survived their solar passage not just intact, but with their activity dramatically enhanced. 3I-ATLAS, however, was not from around here. It was a battle-tested survivor that had already demonstrated a remarkable degree of structural stability simply by enduring its billion-year odyssey through the interstellar void. But it had never before faced a challenge like this. It had spent eons in the near-absolute zero temperatures of deep space, and now it was being subjected to a thermal shock of almost unimaginable violence. The cosmic irony was thick and palpable. After traveling unimaginable distances across space and time to reach our solar system, 3I Atlas would spend its most active, its most revealing, its most transformative moments completely hidden from our view. But in the world of astronomy, patience is not just a virtue. It is a fundamental tool of the trade. And the patient, predictable clockwork of the solar system was on their side. As the Earth continued on its own orbital path, our viewing geometry of the inner solar system would gradually, inexorably improve. The celestial curtain would begin to draw back. By early December, 3I ATLAS, if it had survived, would begin to climb out of the morning twilight, emerging from the solar glare and rising into the pristine, dark skies of a pre-dawn Earth. The hunt would be on. The object's closest approach to our planet was still on track for mid-December, at its calculated distance of approximately 270 million kilometers. And as the date of its reemergence neared, a global coordinated observation campaign was being finalized. The world's most powerful telescopes, from the giant mirrors on Mauna Kea in Hawaii to the sophisticated arrays in the Atacama Desert, were being prepared. Observation time, a precious and fiercely competed for commodity, was being allocated. Instrument packages were being configured. This was not just another observing run. It was an astronomical event of the highest priority. The December observing window would likely represent the best, and perhaps the last, opportunity for our generation to study a pristine sample of intact interstellar material in such detail. Meanwhile, the other members of the September cosmic cast were continuing their own performances. Comet C 2025 R2, the beautiful swan discovery, had faced its own trial by fire as it passed its own perihelion in early November. To the delight of sky gazers everywhere, it had survived. It had emerged from its solar passage, not just intact, but with its tail even longer and more brilliant than before. It was now a confirmed naked-eye object for observers in the northern hemisphere, a beautiful, ghostly smear against the winter constellations, a lingering, ethereal epilogue to the year's more dramatic celestial events. And far beyond, the silent, hulking form of asteroid 99,942, Apophis continued its relentless, gravitationally bound journey. Its 2029 close approach, which had once seemed like a distant, abstract threat, was now just 3.5 years away. The long-term characterization campaigns were well underway, with ground-based telescopes meticulously mapping its surface and radar observatories pinning its bulk to probe its internal structure. Every piece of data gathered now would be an invaluable baseline, allowing scientists to measure precisely how the powerful gravitational tug of the Earth would physically alter the asteroid during its close flyby. NASA's OSIRIS-APEX spacecraft, our robotic emissary to the aftermath, continued its silent, multi-year cruise, its trajectory perfectly calculated to arrive at Apophis in June of 2029, ready to witness, up close, the changes that had been wrought. But the most significant change in our cosmic awareness was still just beginning. The Vera C. Rubin Observatory, having successfully completed its commissioning phase during the autumn of 2025, was now preparing to begin its main survey, a decade-long effort to create a motion picture of the southern sky. Once fully operational, its relentless, sweeping gaze would revolutionize our understanding of the solar system's traffic. It would discover and track millions of new asteroids, providing a level of near real-time monitoring that was once unimaginable. This enhanced cadence would, in all likelihood, finally settle the debate about the September surge. It would show us whether that period of intense activity was a true anomaly, or simply our first clear glimpse of the normal, busy, and slightly chaotic state of our cosmic neighborhood. The drama of 2025, it was becoming increasingly clear, was not just about the arrival of a few spectacular objects. It was about the dawn of a new era of cosmic awareness, an era in which our perception of the solar system was being fundamentally and permanently transformed. The universe we inhabited had not changed, but our ability to see it in all its intricate, dynamic, and sometimes threatening beauty had. And as the first days of December arrived, every eye, both human and robotic, was turning toward the pre-dawn horizon, waiting for the star of the show to make its long-awaited reappearance. The first week of December 2025 was a period of quiet, intense anticipation in the astronomical community. The world's largest telescopes, perched on remote, arid mountaintops, were poised like patient predators, their schedules cleared, their instruments calibrated. In darkened control rooms, bathed in the soft red glow of computer monitors, astronomers drank stale coffee and waited. They were hunting for a ghost. They were scanning the precise patch of pre-dawn sky where the orbital models predicted that 3I Atlas, if it had survived its fiery baptism, should now be emerging from the sun's glare. For days, there was nothing but the familiar, steady starfield. The faintest, most distant galaxies appeared as smudges in the long-exposure images, but of their primary target, there was no sign. A quiet professional anxiety began to build. Had the thermal stresses been too great? Had the object disintegrated completely, its ancient dust scattered into an invisible, undetectable cloud? Had it survived, but with its activity so diminished that it was now too faint to be seen? The models were precise, but they were based on assumptions about an object whose composition and structure were utterly alien. A slight miscalculation in the effect of its outgassing jets could mean they were looking in the wrong place by a few critical arcseconds. Then, on the morning of December 5th, an email alert rippled through the global network. It came from the European Southern Observatory's Paranal facility in Chile, home of the Very Large Telescope. A team, conducting a deep search along the predicted trajectory, had found it. It was a faint, almost imperceptible smudge of light, barely distinguishable from the background noise of the detector. But it was there, and it was moving. It was moving with the exact velocity and on the exact path that 3I Atlas was supposed to be on. The ghost had reappeared. It had survived. A collective global sigh of relief was followed by a frantic, coordinated burst of activity. With its position now confirmed, telescopes around the world could lock on. The James Webb Space Telescope, its golden eye shielded from the sun, swiveled to acquire the target. The Hubble Space Telescope, a venerable and trusted observer, did the same. On the ground, the giant Keck telescopes in Hawaii, the Gemini Array, and dozens of other facilities joined the hunt. The great global characterization campaign had begun. The initial images were tantalizing. The object was clearly a comet, its cometary nature intact. It possessed a distinct, condensed core, the nucleus shrouded in a soft, glowing coma. A faint, but discernible, tail stretched away from the sun, a pale banner testifying to its continued outgassing. It had not been destroyed, but it had perhaps been changed. The initial brightness measurements suggested it was slightly fainter than some of the more optimistic models had predicted, but it was still a viable, active target. The real story, however, would not be told in the images, but in the spectra. The spectrographs, the instruments that act like prisms to break light down into its chemical fingerprints, were brought to bear. And as the first, preliminary spectroscopic data began to stream in from the VLT and the JWST, the story of 3I ATLA's hidden passage began to be written. The extreme carbon dioxide dominance was still there. The comet's coma was still a seething cloud of CO2, a clear and unambiguous confirmation of its formation in an ultra-cold environment. The intense solar heating had not fundamentally altered this primary signature, but there were subtle differences. New, fainter emission lines began to appear in the spectra, signatures of more complex molecules, organic compounds that had perhaps been liberated from the nucleus only under the extreme temperatures of perihelion. The science teams worked feverishly, comparing the new data to the pre-perihelion observations, searching for changes, for any sign of what the object had endured in the glare. Meanwhile, the space-based component of our planetary defense network was also preparing for a major, long-awaited upgrade. While the world's attention was focused on the re-emergence of 3I Atlas, engineers and mission planners at NASA were finalizing the launch preparations for the near-Earth object, NEO Surveyor. Scheduled for launch in September of 2027, this mission was not just another telescope. It was a dedicated sentinel, a guardian specifically designed to hunt for asteroids from a unique vantage point in space. It would not orbit the Earth. Instead, it would be placed in an orbit that trailed our planet as we journeyed around the Sun. From this strategic position, NEO-Surveyor would be able to do something that no ground-based observatory, no matter how powerful, could ever do. It would be able to look back toward the Earth's orbit, scanning the regions of space that are perpetually hidden in the Sun's glare from our perspective. It would be able to detect objects approaching from that dangerous sunward direction, the very blind spot that had allowed the Chelyabinsk impactor to arrive completely unnoticed in 2013. This infrared space telescope, specifically optimized for detecting the faint thermal glow of dark asteroids against the cold background of space, would finally close the most significant and terrifying gap in our planetary defense architecture. Once operational, NEO-Surveyor would provide advanced, and in many cases, years-long, warning of incoming objects regardless of their approach direction. It would eliminate the solar blind spot that represented our single greatest vulnerability. The data from NEO-Surveyor, combined with the relentless, wide-area coverage of the Vera C. Rubin Observatory on the ground, would provide a truly comprehensive belt and braces census of the near-Earth object population. The era of surprises, we hoped, was finally coming to an end. For the amateur astronomers and citizen scientists, the passionate and dedicated volunteers of the Cosmic Neighborhood Watch, the late 2025 and early 2026 period offered multiple, unprecedented opportunities for meaningful contributions to the ongoing research. Comet Swan, having survived its own solar passage, was now a beautiful, lingering presence in the evening sky, and its slow, graceful evolution was a perfect target for modest telescopes and even sophisticated DSLR cameras. Dedicated observers could document the subtle changes in its tail structure, monitor its brightness variations, and watch for any secondary fragmentation events, all of which was valuable data for the professional community. 31ATLAS's December re-emergence would initially favor observers in the southern hemisphere, but its rapid apparent motion across the sky, a result of its high velocity and our own Earth's movement, would eventually bring it within range of northern observers as well in the new year. While the comet itself would likely be too faint for visual observation without substantial telescopic assistance, experienced astrophotographers with sensitive equipment could potentially capture images showing the evolution of its coma, structure, and its complex, multi-component tail. Every image, every data point, contributed to the larger picture. More importantly, the coordinated global observation of these multiple, simultaneous celestial events was providing invaluable, real-world experience in international scientific cooperation and data sharing. The techniques and communication protocols that had been developed and refined for tracking 3.1 Atlas and characterizing the September surge would be directly and immediately applicable to any future planetary defense scenarios, especially those involving potentially hazardous asteroids with dangerously short warning times. The observational challenges of late 2025 were also serving to highlight the critical importance of redundancy and international coordination in our astronomical surveys. It was becoming clearer than ever that no single telescope, no single survey system, could provide complete coverage of all possible approach directions and all possible object types. Only through the seamless coordination between ground-based and space-based facilities, operating across multiple wavelength ranges and at different observing cadences, could we ever hope to achieve a truly comprehensive awareness of our cosmic neighborhood. The events of 2025 were not just teaching us about the universe. They were teaching us how to work together to understand it and ultimately to survive within it. And as 3IATLA slowly, majestically climbed out of the dawn, it was bringing its ancient alien lessons with it. As the last days of 2025 gave way to the new year, humanity found itself standing at a remarkable, and perhaps perilous, inflection point in its long and often troubled relationship with the cosmos. The convergence of our own rapidly enhancing detection capabilities our newly proven deflection technologies, and a growing, if sometimes fragile, spirit of international cooperation was setting the stage for a multitude of possible futures. The dramatic celestial events of the autumn, the unnerving September surge, and the profound revelations of the 3I Atlas encounter were not just isolated astronomical curiosities. They were glimpses, premonitions of the divergent paths that lay ahead, futures that ranged from a triumphant mastery of our cosmic environment to sobering, humbling reminders of our own continued and profound vulnerability. In the most optimistic of these scenarios, the brightest of these forking paths, the technological and institutional foundations that had been so rigorously tested and proven during the 2020s would mature into a robust, reliable, and truly global planetary defense ecosystem. This system would effectively, and perhaps permanently, eliminate the existential risk of major asteroid impacts, while simultaneously revolutionizing our understanding of the broader galactic environment. In this future, the Vera C. Rubin Observatory's unprecedented survey capabilities, working in perfect concert with the spaced infrared detection from NEO Surveyor and its successors, would create a state of near-total cosmic awareness. We would possess a comprehensive, continuously updated catalog of any and all objects on incoming trajectories, with decades or even centuries of advanced warning. This extended lead time, this gift of time, would completely transform the very nature of asteroid deflection. It would no longer be a desperate, high-stakes, last-minute intervention. It would become a routine, predictable, almost mundane form of celestial traffic management. Gentle, precisely calculated nudges, applied years in advance, would divert any potentially hazardous objects onto safe, non-threatening trajectories. These nudges would be delivered by proven kinetic impactor techniques, refined and perfected through a series of multiple next-generation DART-class missions, perhaps even utilizing a standing fleet of rapid-response interceptor spacecraft. The process would become so reliable and so predictable that asteroid deflection would eventually join earthquake prediction and hurricane tracking as just another accepted and expected tool of natural disaster mitigation. It would be a science of quiet, preventative success, a threat neutralized before it ever had a chance to become a headline. Under this bright scenario, the celestial events of 2025 would be remembered as a turning point. Comet Swan, having survived its 2025 perihelion passage, would go on to provide a spectacular, long-lasting naked-eye display throughout the Northern Hemisphere's winter, inspiring a new generation of amateur astronomers, scientists, and engineers. And 3I Atlas, having emerged intact from its own solar encounter, would be studied in unprecedented detail, yielding a treasure trove of insights into interstellar chemistry and the complex, galaxy-wide processes of material exchange. The detailed characterization of 3I Atlas would firmly establish the new field of interstellar archaeology as a major, mainstream scientific discipline. Improved and expanded survey systems, spurred on by the excitement of this first detailed discovery, would go on to detect dozens of additional interstellar visitors throughout the late 2020s and into the 2030s. Each of these new visitors, each a messenger from a different unknown star system, would carry its own unique chemical signatures, illuminating different, unknown aspects of planetary formation around other stars. By the early 2030s, the systematic comparison of this growing library of interstellar debris would provide us with our first comprehensive, empirical survey of planetary chemistry across a wide range of different galactic environments. This scientific windfall, in turn, would drive a new wave of technological development in the fields of spectroscopy, precision astrometry, and the complex art of coordinated multi-telescope observations. And these same advanced capabilities, developed for pure, curiosity-driven science, would prove to be invaluable for the more practical and vital task of characterizing any future potentially hazardous asteroids, enabling the precise determination of their composition, their structure, and their deflection requirements well in advance of any actual threat. International cooperation in this optimistic future would flourish under the shared pressure of these common cosmic challenges. The ad hoc protocols that were developed and refined for coordinating the global observations of 3I Atlas would evolve into standardized, rigorously tested procedures for handling any anomalous or potentially threatening object. Regular, joint international exercises and training programs would maintain a high state of readiness, while simultaneously building a deep institutional confidence in our collective, global response capabilities. Public engagement with the fields of astronomy and space science would reach unprecedented and sustained levels as people from all walks of life followed the ongoing discoveries and the quiet, successful work of planetary defense. The combination of genuine, but managed, cosmic threats and our own effective technological responses would provide a powerful and much-needed piece of compelling evidence for the enduring value of scientific research and international cooperation. But there are other, more challenging, and perhaps more realistic possibilities. An alternative, more moderate pathway acknowledges a hard truth, that our improved detection and deflection capabilities will inevitably encounter real terrifying tests as our catalog of potentially hazardous objects expands. Our current surveys, even with their remarkable successes, have so far managed to identify most of the truly giant kilometer-plus asteroids, the planet killers capable of causing a global catastrophe. But our inventory of the smaller, but still devastating, city killer-sized objects, those in the 100 to 300 meter range, remains dangerously, frighteningly incomplete. Statistical projections, based on the cratering records of the Earth and the Moon, suggest that it is not a matter of if, but when, one or more objects in this dangerous size range will eventually approach the Earth with insufficient warning time for the gentle, elegant, long-range deflection measures of the optimistic scenario. These late detection scenarios, where we have only months or perhaps a few short years of warning, would require far more aggressive and far more risky intervention techniques. They might necessitate the use of more powerful kinetic impactors, or perhaps even the deployment of nuclear explosive devices, a technology that carries with it a host of significant technical, political, and ethical risks. The first such encounter, the first real test of our planetary defense system against a confirmed short-fuse impactor, would be a moment of unimaginable global tension. It would force us to make rapid, irrevocable decisions about deflection strategies under enormous time pressure and the relentless, unforgiving glare of public scrutiny. Success in such a mission would be a triumph, a validation of all the investments in planetary defense, and it would almost certainly trigger a massive expansion of funding for even more advanced detection and deflection capabilities. But failure amiss, a partial fragmentation, an unintended consequence, could result in a regional devastation of unprecedented scale, and it would raise fundamental, agonizing questions about humanity's true ability to protect itself from the indifferent violence of the cosmos. The future, it was becoming clear, was not a single, predetermined path. It was a branching series of possibilities, and the choices we are making now, in the wake of the September surge, would determine which of those paths we would be forced to walk. Even the concept of success in these high-stakes, short-fuse scenarios is a complex and fraught idea. Imagine a deflection attempt that, while successfully preventing a direct impact on a major population center and averting a global catastrophe, fails to eliminate all of the impact risk. An imperfect interception, a kinetic impact that fractures the asteroid instead of cleanly deflecting it, might simply scatter the debris. It could transform one single, large, predictable impactor into a shotgun blast of multiple, smaller, and potentially less predictable ones. The public perception of such an outcome would be a maelstrom of conflicting emotions. Would it be seen as a heroic, last-minute save, a triumph of human ingenuity against impossible odds? Or would it be viewed as a catastrophic failure, dangerous and arrogant, meddling with natural processes that had only made a bad situation worse? The line between savior and culprit could become terrifyingly thin. And then there is the ever-present, statistically dominant, and deeply complex challenge of the ocean. The vast, blue wilderness that covers the majority of our planet's surface is our greatest statistical shield against land impacts. But it is also the source of a uniquely insidious and far-reaching threat. Ocean impacts present a particularly complex set of challenges for both our deflection strategies and our public communication. The brutal reality is that our scientific understanding of tsunami generation from major ocean impacts remains poorly understood, with significant and worrying uncertainties in our current modeling efforts. A 200-meter asteroid, the size of a modest city killer, striking the deep ocean could potentially generate terrifying 10-meter-high waves that would remain dangerously powerful as they propagated across entire ocean basins. A single, catastrophic event in the mid-Atlantic could see devastating tsunami impacts on the coastal cities of 2 continents, from Boston to Barcelona, just hours after the initial collision. In such a scenario, the warning time provided by a successful, last-minute detection might be sufficient for mass evacuation efforts, saving millions of lives. But the economic and social disruption, the complete and utter destruction of coastal infrastructure, ports and cities, would be enormous, even without a single direct casualty from the waves themselves. These scenarios highlight the critical, and often underestimated, importance of accurate risk communication and the management of realistic public expectations about our planetary defense capabilities. Our current technology can, in all likelihood, handle most of the threats we are likely to face, given sufficient advance warning. But the universe is not obligated to be convenient. Late discovery scenarios, or the sudden appearance of an unusually large or structurally challenging object, could easily overwhelm our existing deflection capabilities, leaving us with no good options. And that leads to the consideration of the worst-case scenarios. These are the events that are statistically unlikely to occur on human timescales, the true black swan events, but which represent existential challenges that our current technology simply cannot address effectively. The greatest of these threats comes not from the familiar rocky asteroids of the inner solar system, but from the frozen, ghostly depths of the Oort cloud. A long-period comet, a massive multi-kilometer behemoth, could be nudged from its eons-long orbit and begin its first and final plunge toward the sun. It could arrive with only months, or at best a few years, of advanced warning, its trajectory a ghostly surprise. An object of this scale, with a diameter potentially exceeding 10 kilometers, would carry enough kinetic energy to threaten not just a region, but human civilization itself. It would be a threat on the scale of the dinosaur killer, and it would require deflection energies that are far, far beyond anything that is achievable through our current kinetic impactor techniques. Theoretically, a nuclear explosive deflection might be possible. The immense energy of a nuclear detonation, used not to shatter the object, but to vaporize its surface and create a powerful, rocket-like thrust, is the only tool in our arsenal that could conceivably alter the path of such a monster. But the required technology development, the international coordination, and political agreement needed for such a mission, and the complex deployment timelines, could easily exceed the very short warning periods that these long-period comets provide. These extreme, but not impossible, scenarios serve as a stark and humbling reminder that our planetary defense systems, as impressive as they are becoming, provide us with protection against most threats, not all threats. Like the earthquake-resistant building codes that protect a city against most tremors, but not the big one, or the hurricane tracking systems that give us warning but cannot stop the storm. Our defensive measures can dramatically reduce our risks without ever eliminating them entirely. The goal is not, and can never be, perfect security, an impossible, and perhaps undesirable, standard. The goal is a more modest, but far more achievable one. reasonable protection against the reasonably likely threats. And into this already complex calculus of physics and technology, we must add the most unpredictable variable of all, us. Population psychology and the complex, often irrational, dynamics of human societies introduce a layer of profound complication across all of these potential scenarios. The public reaction to a credible asteroid threat would depend heavily on the strategies used for risk communication, the patterns of media coverage, and the pre-existing levels of trust in our scientific and governmental institutions. Accurate, timely, and transparent information, provided by credible and trusted sources, could maintain social stability and enable effective, coordinated action during a crisis. But sensationalized, fear-mongering reporting, or the inevitable and rapid spread of conspiracy theories, could just as easily undermine the effectiveness of our response, even when our technical capabilities are perfectly adequate for the job. The September surge of 2025 had provided us with a valuable, low-stakes opportunity to test and practice the delicate art of managing public communication about cosmic threats. But a real impact scenario, with lives and cities hanging in the balance, would involve much higher stakes and a far more intense, and potentially more chaotic, media scrutiny. The powerful, algorithmic amplification of both accurate information and deliberate misinformation on social media could significantly, and perhaps disastrously, complicate any crisis management efforts. The economic implications also vary dramatically across these different, branching futures. A successful and publicly visible deflection of a major threat could generate enormous and sustained public support for continued and even expanded investment in our planetary defense capabilities. But a failed or even just a partially successful intervention might trigger a more cautious and perhaps more fatalistic public approach, one that emphasizes passive measures like evacuation and damage mitigation over the more active and potentially more risky strategies of deflection. The choices we make in the aftermath of a crisis will be just as important as the ones we make during it. And as the new year dawned, the universe had just reminded us that such a crisis was not a matter of if, but of when. Into this intricate, high-stakes ecosystem of science, survival, and social psychology, a powerful new force was beginning to exert its influence: commerce. The growing involvement of the private, commercial space industry in asteroid-related activities was introducing a set of market dynamics that could either powerfully support or dangerously complicate our collective planetary defense efforts. The same wandering mountains of rock and metal that posed a potential existential threat to life on Earth also happened to be treasure chests of unimaginable wealth, floating freely in the vacuum of space. They were rich in the very materials that fueled our terrestrial industries: iron, nickel, cobalt, and most tantalizingly, the platinum group metals that are incredibly rare on Earth's surface, but are thought to be abundant in certain classes of asteroids. Private companies, motivated by the staggering potential profits of asteroid mining, were beginning to develop the very technologies and capabilities that served a dual purpose for both resource extraction and planetary defense. The ability to travel to, rendezvous with, and physically interact with a near-Earth object is the fundamental requirement for both mining and deflection. The advanced characterization sensors needed to identify a resource-rich asteroid are the same sensors needed to determine the composition and structural integrity of a potentially hazardous one. A commercial prospecting mission could, in theory, provide the invaluable, close-up data needed to plan a successful kinetic impactor mission. The profit motive, that powerful and relentless engine of terrestrial innovation, could become an unexpected and potent ally in our efforts to safeguard the planet. But commercial priorities do not always, or even often, align perfectly with the needs of public safety. A potentially hazardous asteroid that also happens to contain trillions of dollars worth of accessible platinum might suddenly face a set of competing and potentially conflicting claims from both mining consortia and planetary defense agencies. These conflicts, which once seemed like the stuff of far future science fiction, were now becoming a plausible, near-term reality. They would require the careful, and probably contentious, development of new international regulatory frameworks to balance the powerful allure of commercial interests with the non-negotiable requirements of public safety. Who owns an asteroid? Who has the right to move it? And who is liable if that move goes wrong? These were no longer abstract, philosophical questions. International politics, however, remained perhaps the most unpredictable and most dangerous variable in any of these future planetary defense scenarios. The current, carefully constructed mechanisms for international cooperation, like the International Asteroid Warning Network, were working well during the calm, routine periods of observation and data sharing. But a genuine, time-sensitive crisis involving a potential impact on a populated area might trigger a very different and much more competitive set of nationalistic responses. Countries, driven by self-interest and a desire to project strength and technological prowess, might be tempted to pursue their own independent, unilateral deflection efforts rather than coordinating through the established international frameworks. This could, in a worst-case scenario, create a chaotic and counterproductive situation, with multiple, uncoordinated interventions potentially working at cross purposes, or even making the impact threat worse. The trajectory of our own technological development will also profoundly influence which of these scenarios becomes the most likely. Breakthrough advances in seemingly unrelated fields, new forms of high-efficiency fusion propulsion, revolutionary advances in artificial intelligence and autonomous robotics, or the development of new, ultra-lightweight materials could dramatically and unexpectedly expand our deflection capabilities and extend our effective warning times. Conversely, a period of technological stagnation or a significant reduction in public funding for the space-based detection systems that are so critical for early warning could leave us dangerously vulnerable to the very threats that our current projections assume we will be prepared to handle. And in the great global competition for resources, planetary defense must always contend with more immediate, more visible, and often more politically potent challenges. Climate change, pandemic preparedness, economic inequality, environmental degradation, and the constant, simmering threat of international conflicts all compete for the same limited financial and political resources. The public and governmental attention has a finite and often tragically short bandwidth. An asteroid threat that seems abstract, distant, and statistically improbable might easily lose priority relative to the more immediate, tangible crisis of the day. Planetary defense, like a city's flood walls, is an investment that can seem unnecessary and extravagant right up until the moment the waters begin to rise. Yet the unique, almost spiritual, cosmic perspective that is offered by the study of objects like 31ATLAS provides a rare and powerful opportunity to transcend these terrestrial divisions and to refocus on our shared human interests. The raw, humbling knowledge that our planet, our only home, exists within an active and sometimes violent galactic environment that is filled with both potential threats and profound opportunities could act as a powerful catalyst for global cooperation in ways that purely terrestrial challenges often fail to achieve. The sky is not national. An incoming asteroid does not carry a passport. The threat and the wonder are universal. As we stand at the threshold of these potentially revolutionary improvements in our ability to monitor and manage the cosmic threats that share our solar system, the futures that will ultimately emerge will depend as much on our social and political choices as they will on our technological capabilities. The September surge and the remarkable encounter with 3I-ATLAS were serving as both a powerful inspiration and a stark, unambiguous warning about what lies ahead in humanity's long and evolving relationship with the broader cosmic environment. But before any of these long-term, speculative scenarios could unfold, we first had to learn what 3I-ATLAS itself had come to reveal. We had to read the message that it had carried across the void. And as the astronomical community began its intensive post-perihelion analysis, the chemical signatures and the physical properties that were being documented during that crucial December observation window were poised to provide us with our first truly detailed forensic glimpse of authentic, pristine material from another star system, and our first real tangible understanding of what it truly means to be citizens of a galaxy where worlds and the very stuff of life are constantly being exchanged across the vast, dark, and silent distances between the stars. As the winter of 2026 settled across the northern hemisphere, and 3I Atlas began its long, slow, and now closely watched journey back out into the interstellar dark, we found ourselves at a remarkable, and perhaps historic, inflection point in humanity's long relationship with the cosmos. The celestial events of autumn 2025, from the menacingly close approach of asteroid 2025 FA22 to the beautiful ghostly display of Comet Swan, to the profound discovery and detailed characterization of our third confirmed interstellar visitor, had provided us with something far more valuable than just a trove of new scientific data or a successful validation of our planetary defense systems. They had given us something much more fundamental, a new lens through which to view our own place in the universe. For the vast majority of human history, the night sky had appeared as a thing of eternal, static, and predictable beauty. The stars wheeled overhead in their majestic, unchanging patterns. The planets, the wanderers of the ancient world, moved along their own complex, but ultimately predetermined paths. The occasional startling appearance of a comet or a fleeting, brilliant shooting star served as brief, transient reminders that the space between the worlds was not entirely empty. But this perspective, born of our limited, earthbound viewpoint, had fostered a deep and pervasive sense of cosmic isolation. The Earth and its inhabitants, our triumphs and our tragedies, all seem to be the unique and solitary products of purely local stellar processes, fundamentally and perhaps permanently separated from the rest of the galaxy by unimaginable, unbridgeable distances and timescales. The September surge and the arrival of 3ITLAS had shattered that ancient, comfortable illusion of isolation. In the space of a few remarkable months, we had discovered that our solar system is not a quiet, isolated suburban neighborhood on the forgotten outskirts of cosmic activity. It is, in fact, a busy, bustling, and sometimes chaotic intersection, a cosmic crossroads where ancient travelers from distant, unknown worlds regularly pass through, carrying with them the silent, elemental messages of their origins. The object known as 3I Atlas in and of itself represents a direct physical connection to the stellar and planetary processes that occurred billions of years ago in regions of the galaxy that we may never ever visit with our own spacecraft. It was a piece of another world delivered. This represents more than just a scientific revelation. It constitutes a fundamental, and perhaps irreversible, shift in our cosmic perspective, a change in our understanding of our own context that is comparable in its significance to the Copernican revolution, which first displaced us from the center of the universe, or the later discovery of the expanding universe, which revealed the true staggering scale of space and time. We now know, with a certainty born of direct observation, that we are not the isolated, self-contained products of a single special stellar system. We are, in fact, active participants in vast, galactic-scale processes that have been exchanging materials, and perhaps even the chemical precursors to life, between worlds for longer than the Earth itself has existed. The strange alien chemical signatures that we had found preserved in the ancient frozen ices of 3I Atlas carry with them direct physical information about the stellar nucleosynthesis rates, the planetary formation conditions, and the volatile chemistry that existed in an environment that was born before our own sun began to shine. Every spectroscopic observation, every single data point we collected, provided us with a direct sampling of the processes that shaped our galaxy during its turbulent and creative youth, a time when star formation rates were dramatically higher and the distribution of the heavy elements was vastly different from the configuration we see today. But perhaps most importantly, the events of autumn 2025 have demonstrated, beyond any doubt, that we now possess the technological capability to not only recognize and study this galactic scale system of material exchange, but to potentially interact with it. The very same detection networks that had so successfully tracked the close approach of asteroid 2025 FA22, and which will be used to monitor the 2029 flyby of Apophis, have also proven that they can identify and characterize interstellar visitors like 3I Atlas with sufficient precision to extract a wealth of detailed forensic scientific information. We have, in a very real sense, graduated. We have transitioned from being merely passive, awestruck observers of cosmic phenomena to becoming active participants in the new science of interstellar archaeology. Every new survey telescope that comes online, every improved spectroscopic technique that gets developed, every new international cooperation agreement that gets signed brings us one step closer to a truly comprehensive understanding of our galactic neighborhood and our own intricate role within it. And this profound transition carries with it implications that extend far beyond the specialized fields of astronomy and planetary defense. The vast complex infrastructure that is required for the effective monitoring of cosmic threats and the detailed study of interstellar visitors, the high-precision detection systems, the rapid response, characterization capabilities, the seamless international coordination mechanisms provides us with a powerful and perhaps unexpected template for addressing other more terrestrial global challenges. The existential threats of climate change, the rapid and coordinated response required for global pandemics, the sustainable management of our planet's finite resources, and the protection of our fragile global environment, all of these challenges require a similar and often identical combination of deep scientific understanding, advanced technological capability, and a robust framework for international cooperation. The very same lessons that we are learning from the process of tracking asteroids and characterizing comets could prove to be equally and perhaps vitally valuable for the process of monitoring global greenhouse gas concentrations, predicting the spread of infectious diseases, or managing our shared and increasingly stressed ocean and atmospheric resources. The view from space, it turns out, gives us a powerful perspective on the problems we face here on the ground. The choice is ours, whether to heed the lessons that the universe is so generously, and sometimes so terrifyingly, providing. More fundamentally than any specific technology or protocol, the cosmic perspective that is fostered by our newfound awareness of interstellar visitors like 3I Atlas offers a potent and perhaps necessary antidote to the kind of short-sighted parochial thinking that so often hampers our attempts at cooperation on global issues. When we truly and fully recognize that our Earth exists not in isolation, but within a dynamic, interconnected galactic ecosystem, one where material constantly and naturally flows between stellar systems across vast, almost unimaginable distances and timescales. Our own terrestrial divisions, our borders, our ideologies, our economic systems begin to seem profoundly, and perhaps even absurdly, insignificant. We are all, every single one of us, passengers on the same small, fragile planet, threading its way through a galaxy that is filled with the ancient wandering debris from billions of other worlds. The very carbon atoms that form the basis of our bodies were forged in the nuclear furnaces of stars that lived and died before our sun was born. The water that we drink, the substance of our life, may have arrived on this planet via the impacts of comets that originated in the cold, dark outer reaches of our solar system. The air that we breathe contains elements that have traveled between the stars for longer than complex life itself has existed on Earth. This is not poetry. It is a scientific fact. This deep physical understanding of our own cosmic heritage has the power to transform our approach to the challenges we face. Environmental protection and social cooperation are no longer just abstract moral imperatives. They become practical, logical necessities for responsible cosmic citizenship. We cannot, and we must not, afford to waste the rare and precious conditions that allow for the flourishing of complex chemistry and biological evolution on the surfaces of planets. Nor can we afford to fragment our collective response capabilities through short-sighted competition when we are confronted with challenges that operate on galactic, not national, scales. The September surge and the mysteries it presented have also served to highlight just how much we still do and know about our own cosmic neighborhood and the physical processes that govern it. Our current models, based on the handful of interstellar objects we have so far detected, predict that these visitors should be relatively rare, perhaps one detectable object every few years under optimal observing conditions. But what if those models are wrong? What if 3I Atlas represents not an exceptional, once-in-a-generation event, but a new and more accurate baseline for the true level of interstellar activity? If that is the case, then our current estimates might be off not by a small factor, but by orders of magnitude. The Vera C. Rubin Observatory and the other next-generation survey systems could soon reveal that dozens or perhaps even hundreds of interstellar objects pass through our solar system. Annually, most of them too small, too dark, or too fast to have been detected with our previous less sensitive technology. This would completely transform our understanding of galactic material exchange rates. It would also raise profound and thrilling questions about the prevalence of complex organic chemistry, and potentially even the simplest forms of biological processes throughout the galaxy. If interstellar space is indeed filled with a constant, gentle rain of organic compounds and volatile materials that originated in a diverse array of different planetary environments, then the very ingredients for life might be distributed far more widely and far more generously than we currently realize. Every comet that enters our solar system, whether it is a local traveler from our own Oort cloud or an alien messenger from a distant unknown star, carries with it a physical analyzable sample of the chemical conditions that existed at the time and place of its formation. These natural, perfectly preserved laboratories provide us with direct access to processes and environments that remain far beyond the reach of our most ambitious and most expensive robotic spacecraft missions. But to study these cosmic messengers, to read the stories they carry, requires a continued and unwavering investment in the full spectrum of detection, tracking, and characterization capabilities that made the remarkable discoveries of 2025 possible. The technologies and the international institutional frameworks that allowed us to identify 31ATLAS as an interstellar visitor and to track the safe passage of asteroid 2025. FA-22 represent the culmination of decades of patient scientific development and hard-won international cooperation. These precious capabilities are not self-maintaining. They require ongoing funding, constant technological upgrades, and the sustained political support from governments and institutions worldwide. The long, quiet intervals that can exist between major impact threats or the appearance of spectacular interstellar visitors can make it tempting to reduce our investments in these planetary defense and cosmic surveillance systems. That, we now know, would be a profound and potentially catastrophic mistake. The September surge has shown us, with a clarity that cannot be ignored, that our cosmic neighborhood is far more active and far more interconnected than we had ever previously realized. We are, at this very moment, finally developing the observational and analytical tools that are needed to truly understand our place within these vast, galactic-scale processes that have been operating silently and unseen for billions of years. The coming decades could witness revolutionary advances in our understanding of planetary formation, stellar evolution, and galactic chemical evolution, all based on the direct, physical sampling of interstellar materials that are being delivered, free of charge, directly to our telescopes by these natural cosmic processes. But this will only happen if we maintain and expand the capabilities that made these initial discoveries possible. The choice that now lies before us is as clear as the star-dusted sky on a moonless night. We can choose to embrace our emerging role as cosmic citizens, investing in the technologies and the international institutions that are needed to monitor and to understand our galactic environment, while simultaneously protecting our precious home planet from the very real cosmic threats that exist within it. Or we can choose to retreat into our old familiar terrestrial parochialism, abandoning this new profound cosmic perspective just at the very moment when we are beginning to glimpse the true, staggering complexity and wonder of the universe we inhabit. The September surge and the remarkable encounter with 3I Atlas argue powerfully, and perhaps even urgently, for the first path. We have been given unprecedented opportunities to study authentic physical samples from other star systems, while at the same time demonstrating our own growing capability to protect the Earth from cosmic threats. These achievements, taken together, represent nothing less than the beginning of humanity's long-awaited transition from a planet-bound species to active and responsible participants in galactic-scale phenomena. But this transition will only succeed if we manage to maintain the curiosity, the cooperation, and the deep, unwavering commitment to scientific understanding that made it possible in the first place. The cosmos has delivered a set of remarkable and priceless gifts to our telescopes and our detection networks. Whether we, as a species, prove to be worthy of these gifts will depend entirely on the choices we make in the months and years that lie ahead. The real adventure, the great work of cosmic archaeology and interstellar understanding, lies before us, waiting for us to develop the wisdom and the spirit of cooperation that will be needed to read the silent ancient messages that wanderers like 31 ATLAS carry across the dark and beautiful spaces between the worlds. What's your number one theory about the September surge? A cosmic coincidence or something more? Drop your thoughts in the comments. I want to hear them. And if you love untangling the universe's greatest mysteries, subscribe and ring the bell to join our crew of cosmic detectives on the next case.